Yay. All right. Cool. 115 participants. Cool. Hello, everybody. I'm going to share my screen. Swabi says hello. Vignesh says hello. I have not seen this chat window yet. Ritika, yes. Jinhao, Shreya, Bamik. Hey, cool. Everybody. Hi. Jinjin, Rangapriya, Shobit, Sri Sayed, Shriyag. Cool. Okay, so let's actually start. Share the screen. Ooh, I like this. This is actually very good. Okay, so first of all, it's a little bit of sweet Indian dessert for you that makes you hungry. For people that don't know, this is called Gulab Jamun. It actually says that right here somewhere. Where does it say it? Gulab Jamun, right there. Gulab Jamun. It's so yummy. All right. First things first, always. Don't forget your dessert. Life is uncertain. Eat your desserts first, actually. You never know. So more is blinking. Chat window. Ooh, tempting or jumbo for the Gujaratis. Oh, I did not know that. Yeah, I know. Tell me about it. The best sweets. Yes, yes, yes. Very cool. You guys are funny. Okay. So I'll put up our window. So we have some fun things to talk about. Particularly, we're going to talk about being so normal. I said abnormal is bad. Rasmalai. And we'll talk about SQL. So we're not behind. I can show you the syllabus in a little bit. I had actually padded, maybe put in some time for this kind of an extra delay, but now we can make use of the time so nothing is lost. OMG, look at that. It is so shiny, it's so silvery, it's so good. So shiny, look at it. The liquid is actually liquid butter and sugar. OMG, it's liquid heart attack if you're not careful. Fried dough balls. Yeah, mouth-watering. So I try to get some of the liquid stuff going on right there with the shininess. Okay. Yeah, so there's that. And then there's also something else. We should put up our course page and start. Mouth-watering. Srinidhi says, I want some now. Yeah, I definitely enjoyed every piece of it. Thank you. Although I still have a tiny bit of the gulab jamun still left. But check this out. So the color changed. It's like, Valentine's red. Check that out. There's a little SQL query there for you. So a tiny bit of a, grammatical error, but we can't change SQL. But that's funny, right? So I hope not. I hope it's better than that for you. But there's a little bit of SQL joke for you. And then, ooh. Gua Niao Hao. Xinyang Kuai La. Yeah. Cool. So the Chinese New Year is on Friday. It's the year of the ox, but since we're not going to meet till next Wednesday, exactly. Happy Lunar Year. Happy Spring Festival. A couple of years ago, my friend Lurong was here, so when I had all kinds of really cool Chinese sweets. I had no idea they had so many desserts in China. Oh my God. Lotus wasn't a big lotus flower leaf thingy. It's pretty cool. Okay. So back here, I put up one extra thing in here. Oh, cool. Look at all that. I love it. Wow. Very nice. You guys can, this is all Unicode, you can paste it in here and it's what actually happens. Okay. So this one is at Rice. They're starting this, Masters in Data Science. They call it MDS. And the reason to put that up is the data science has the word data. So if you look through all of this, they actually tell you some of the courses, are basically like database, data related. See, like the big data, programming, you already know that's some machine learning, data visualization. So in this course right here, we're actually going to cover some of this, okay? Because all of machine learning, supervised machine learning, and the data science go right back to data. So it all starts with data. So that's the second half of the course, actually. Speaking of second half, the homework is going really well. I see like all kinds of Piazza posts, which is good. A few people wonder about EER. Yes, in that description, you can find a place or a couple of places to actually use EER if you want. And none of the existing software tools might have the symbols to draw the circles and the double line or the single line at the bottom. You can do that in Photoshop or any old, image program. I use something called OpenView that is right here. So you can, do anything really. And so you can make it work, or you don't have to use it. Okay. Okay. So today, these are topics I'm going to launch into it. All right. So I used to have a bumper sticker in my car that said exactly this: why be normal? And yes, that sticker was upside down. So, being normal, is overrated, okay? It's okay to be a little bit strange. Not too strange, a little strange. So there's idea of normalization. So why do we force tables to be normal? So what does normal even mean? In databases, in entities, in one table really, or normalization you apply to just only one table. You don't apply it to the whole ER diagram. There's no such thing. You do this process. It's a process. You do the process table by table by table. And the reason to do this process for a table is because you want the table to be clean. You don't want the table to be badly designed. So normalization is a process to create clean design. And why would you not want that, right? So, that's our goal. Our goal is to create the best possible design so that even after 10 years, 20 years, it continues to work. There's nothing to improve. So how do you systematically make sure that you have done a good job? That is what normalization is about. A very tiny table that just has 3 columns, you don't have to do normalization. It probably already is okay. But real world tables, Amazon's customer table, they have more than 120 attributes. Just think of that, okay? So per an Amazon customer, they know more than 120 columns of data per row. And so when you have a table that large, you need to really make sure that, the table is as well designed as it can be. So that is what the normalization process is. So I'm going to talk you through that process. And then there's the notion of denormalization. Sometimes normalization is too much. So then you want to reverse it. That is called denormalization. So we'll do that at the very end. The table of contents looks like this. So pretty much it's all normalization, but maybe the last couple of slides we just talk about denormalization. If you press the letter C, C stands for table of contents. C, 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 C is just a toggle. And you can jump around anywhere you want, okay? The process is right here. Okay, but we'll go in sequence. So on top means what is planned for today. We have normalization, what role it plays in the design process. So first of all, you can do normalization. You can carry out this process while you are doing your ER diagram. That might be the very best time to do it. Even for this homework, you're welcome to do the normalization on your own tables and submit it after you normalize. Then you'll have a clean design. But in this homework, one will not penalize you for a so-called bad design. Bad designs are okay. We cannot expect, somebody who is just doing it for the very first time to say you have to create the best design. But if you care, you can go through this process yourself and make sure that your design looks good. So it's a design process. When you normalize, what happens is our tables turn into certain forms, meaning our table look a certain way. So one way the table looks is called the first normal form. So that's one step in the first step in normalization, actually. It's called the first normal form. Usually we don't stop at the first normal form because it is almost like, it's no big deal. It's very easy to do. So from first normal form, you clean it up a little bit more. Then the result is called a second normal form. That's also good. It's obviously better than first normal form. But then that is really not the place to stop. We should look one more time to see if we can go from second normal form to third normal form. Sometimes the second normal form and third normal form are the same. There's no change to make. So then you're done. Otherwise, if there's one more change you can make, then you would make that change and then come up with the third normal form. And after that, you can stop. You can, give it to your client and you can walk away. Because theoretically speaking, just for research purposes, for database design, philosophy, the theory of database design, there are even more normal forms, BCNF, 4NF, there's even 5NF. But then if you do all of that, and what happens is your database queries that people perform on your tables will get really, really slow. So then it becomes pointless. You have a super clean design, but then people hate your design. So that is why we stop at 3NF, okay? So after 3NF, there's really no point in doing it anymore. Okay. So normal forms are transferred from lower to higher. We always systematically go from 0. There's even a 0 normal form, which is completely unnormalized. So 0 to 1, 1 to 2, 2 to 3. That's what I'm going to teach you today. And it's very intuitive. It's very simple, very straightforward, and very reasonable. In other words, these rules don't exist for no reason. They exist for a very good reason. You want a good table. So hopefully it'll make so much sense to you. You can see the example I'm going to show you. And then, so this is the point that I just mentioned. The best time to do it is concurrent at the same time. So when you're doing your modeling like homework 1, do it then, because you can let a few years go by. And so for those few years, you've given somebody a bad design. and afterwards you charge more money to normalize it and make it a better design. That's probably not the right thing to do. So the right thing to do is while you're doing the ER, diagrams. Okay, but you can do it afterwards if you want. If you've done a great job with the ER diagram, then there's zero normalization to do. It's already in 3NF. Okay, then all this goes away. All this only happens when you have bad, like a lower quality table. Okay, and then denormalization is just for efficiencies. I'll tell you about that afterwards. So therefore, an unnormalized or a lower normalized table is loosely like a ball of yarn, that is not carefully balled up. It's like tangled up. Like, whoa, look at this, it's a mess. So tables can also be like a mess. Some designer can look at that and go, wow, who designed this? It's horrible. So then after you normalize it, then everything would look so clean and people would appreciate it. So loosely, that is the idea of normalizing. You're cleaning up tables. Also, this illustrates one more thing, by the way, which is this all looks like one big ball of yarn. And then when you're done, you clean it up. It looks like 4 different balls of yarn. That is actually what happens in normalizing. So if normalizing were to happen, if it is required, a single table will actually break up into multiple tables. Okay. So, in your homework, this might happen. You might have a table of staff or something. After you normalize it, suppose you need to normalize, then you would end up with more than one table. Okay. So in general, you cut it up. And that is actually what causes the normalization. So you almost intuitively know pretty much what I'm going to tell you. And then we can go fast after that. All right. Oops. No devices. All right. So again, evaluating, correcting table structures. It's all about the columns, okay? It is not even just about the columns. It is all about dependency. It is about primary keys and non-primary keys. It goes right back to the idea of full functional dependency. So we want every single entity, an entity you are trying to normalize, you want that entity to display full functional dependency. It means if there's one primary key column, then the primary key column is the only column that decides all the other non-primary key attributes. Like your student ID should tell us everything about you. That's easy. On the other hand, when you have a composite primary key, say first name, last name, stuff like that, when you have 2 columns, even 3 columns for a primary key, all those columns should be required. There should be no case in a table. In other words, there should not be a situation where you have a 3-column composite primary key, but only one of those columns, that information there, is enough to decide something else. Okay, that's called a partial dependency. If that happens, the table needs to be normalized. So you keep on normalizing till you only have full functional dependency. Okay, that is basically the summary of normalization. It's pretty simple. So when you go from 1 to 2, 2 to 3, you're trying to get rid of all the situations where, where what I said is not true, where full functional dependency does not exist yet. After third normal form, all the individual little tables you end up with, each one of them will have full functional dependency. Then you stop because there's nothing better to do. Cool, right? Easy. And then again, if you leave tables unnormalized, what is the problem? Why should I even normalize? First of all, it's ugly design-wise, but it also leads to lots and lots of data being repeated all over the place. So it's all about cleaning up data so you keep a piece of data in only one place and others can simply refer to it. When you have the same piece of data in multiple places, you can start to have problems. It's like copying and pasting code, and you had a bug, except you copied and pasted the code 5 times. You only fixed the bug in 4 places. You forgot to fix the bug in the 5th place. So now you have a new bug that's probably hard to find because only when you get that 5th place situation, the bug is going to show up all of a sudden. So we don't want code to be repeated. You want to abstract code away and make a function call. It's like that. So to reduce anomalies in data, you don't want to keep the same, you don't want to repeat anything at all over and over for multiple rows, okay? So that's again like a high-level summary of what we're going to do. So the higher-level forms lead to more and more clean design. So third normal form is as clean as it can get, practically speaking. And then you can break it up even more, but then it becomes too much broken up. And then joins take like too long time to run. All right, so again, higher normal forms are better than lower. Properly designed 3NF meet the requirement of 4NF. Yeah, so 4NF is hardly encountered in real life, You can read up on 4NF if you want, okay? Just go there and type DB space 4NF and stuff will come up. So denormalizing goes backwards. If you normalize too much, meaning, if you do all of this correctly, your initial long table that had all the data that ran really fast, everything was in one place, will now become multiple data, multiple tables really, and then you have to join when you do SQL queries. So joining is gonna make things slower. Therefore, you can denormalize. You can, put the tables back and make them one big table, meaning make your design look bad on purpose. But it'll lead to increased performance. So you cannot have good performance and also good table design. Sadly, you got to pick one. Okay, that's all. So normalization is a design step. I've said this before, and so you use it normally when you design a new database. See, when Amazon started right in '96, they thought about what they're going to do, but they couldn't think of Amazon Prime, and all the other businesses they now support. All that came afterwards. So in a big company like that, there's constantly a need for designing new tables. Or Facebook buys WhatsApp, and all of a sudden they have a new business, or Instagram. So those are all examples of even in today's world, there's a need for a clean new design from scratch. Wow, what should I put in our tables? Then you should do a good clean job of normalizing. Yeah, right, exactly. That's actually true. I mean, unfortunately, in the real world, what happens is when you normalize, it's a good clean design, but then your queries will run slower than before. And then if somebody complains too much, then you're forced to put back what you had, like revert it, just basically go back to an old version of your repo, just undo all your changes. It doesn't, feel good, but then the users are king, right? Users are queen. What is the point of having this amazing database if every time you hit search you ask a question about a laptop and it takes 10 seconds to come up with the answer? People will just say, screw that, I don't want your laptop. So that's the problem, right? You need to give what the customers want. All right, so we'll use this one example over and over, which I'll put up in the next, tab like this. It's a cool, fun little table that says, what is the problem with not normalizing, and then how can we fix it? All right, so employees of a construction, then why is there a need to normalize? Just to make a clean design. It's really a design deal. Even with function calls, if you make way too many function calls, suppose you had a main function, right? Your main function. The main function did some image processing. You're doing some cool filters on, maybe the art here. And then say I want to blur it. It takes like 5 seconds. So now I go crazy with software design and I make so many cool function calls. And finally, there's one function call per pixel. Just keep on calling functions. Then next time I want to blur it, it may take me like 5 minutes to blur the same image. I'll go, oh my God, what did I do? And I throw away all my functions and go back to my big main function. That's the same answer. So you like to do it because it's a good idea, okay? But then it's not good for people to use it. So therefore, you might not do it in the real world. I'll give you a better answer, okay? It depends on the table. It depends on your customers. When you have a small company with few limited customers, few limited users, I think you should normalize. But then the bigger the table gets and the more you break it up, then more people will complain, and then you shouldn't do it. So there's no one answer, to why should you do it or not. In fact, try it, and then if people complain, then you can always go back. Then you'll be a hero. Wow, see, I gave you back what you wanted. Okay, so there's a construction company, engineering firms, right, like Larsen and Toubro, Schlumberger. They all go all over the world and work on multiple projects. They have thousands of employees. Suppose you have a system like that, a construction company. Suppose this is the only way that they maintain information about who works and what, and where, what, all the details, right? Supposing this is the initial table. We'll use this example to say, why is this bad and how can we normalize it? Is the kind of balance give it some denormalization? Yeah, correct. That is exactly right, okay? So you can denormalize selectively. If some joins are slower, then only denormalize that part. Again, it's a continuum, not, one or the other. All right. So suppose, the construction company has many projects simultaneously going on. They work all over the world. And projects have a primary ID, like a project number. So here, there's 4 distinct project numbers. Projects also have a human understandable names. How is the Evergreen project going? So rather than numbers, you give names to things. This for human readability. And then each project, so there are 4 projects currently they're working on. And employees can share their time between projects. Suppose you're an architect, then you can sit in your same desktop, all day. But you could be designing a part of one building for one project and then switch to another project in the afternoon. So therefore, you need to know for that project who are the employees. So employees have IDs, like 103, for example, is over here, and then 103 might be somewhere else. Look at 105. So 105 is here, 105 is also here, as an example. Okay, so employees can share, the time between projects. And employees obviously have names, so the employee number and the name go together. Every time it says Alice K. Johnson, it's 105. Again, same thing. Hopefully, it's the exact same thing, Alice K. Johnson. And then also employees have job titles because it's going to, give them certain dollars per hour. So then for every employee, you list what their title is. And again, it's the same throughout the table. Alice is a database designer, so obviously the same Alice, same database designer, and those things don't change. And this is, again, if you're a certain job category, how much money, should you charge the client per hour? So the electrical engineer June is able to charge the Evergreen project $84.50 per hour. And it's the same rate, same thing for anyone else. So if you see June somewhere else, okay, then it's going to be the exact same amount. I'll pick Alice Johnson again, $105. See, database people get paid the most. So then the same $105 per hour applies no matter where she is, okay? So if you work on, this is somebody else, database designer. But you get the idea, right? So the job titles come with certain rates. And this information is very key. This is what says for a given project, for a given employee, maybe this is, per week or something. How many hours did they put in, for that project for that week? Because then at the end of the week, you can multiply that by charge per hour and then know that much amount to charge to that client. So you do this row by row by row, and every row times, how many hours will be charged to, that particular project. Yeah, exactly. Well, because because of machine learning, whatever code you want to write, some software can just spit it out. So programmers are slowly becoming a dead entity. So don't be a programmer. It depends on the type of programming, honestly. Things like web designers are a dime a dozen, okay? So if you pick something that is pretty good, yeah, then you'll get paid a lot. Programmers like to commit suicide for future programmers. It's a very strange form of suicide, where you make future people's jobs harder. In other words, people are writing code now that will actually make future programmers obsolete. I'm not kidding. All right, so get back here, okay? Each employee has an ID, they have a name, they have a title, and they also, because of the title, how many hours, how many dollars they make per hour. On projects, they have a number, they have a name, and then who are the assigned employees. So it makes sense, what I told you. And each employee can be assigned to more than one project. And the company bills the clients for projects. If you want to know how much money we're making from Evergreen, take all these projects and then multiply the rate by the number of hours worked. Then you'll have one subtitle, like one subtotal for Evergreen. And then how much are we charging Emberware, how much Rolling Tide, how much Starflight. And finally, this is how much the construction company is making from all those employees. Add those four subtotals. That's really what they want to do. So yeah, actually make it a little bit bigger here. Why not? Oh, it got smaller. Okay, you can always fix these. So here. All right, so this is the thing that I just now told you, okay? At the end of the month or at the end of the week, what you want to do is just simply literally multiply. So you just take that amount and multiply 84.5 times 23.8 is that 105 times roughly 20. You see that? And so then for that project, just add up all of them. And that is how much money we're making off of this client right here, Evergreen. And likewise, Emberwave. So 4 subtotals. And finally, that is the whole grand total. These are the kinds of reports that people run all the time, just to see how much money we're making. Okay, so there's nothing wrong with, how this is working. Obviously, it seems to work. There's no numerical errors. But we shouldn't do this, though. We should not leave this table the way it is. It's a very bad idea. So why is it a bad idea? What makes this, a bad design? So I'm going to show you. Okay, so next slide. Issues with our database, okay? So the same picture that you saw before. This is really an Excel spreadsheet, okay? So in many construction companies, unless they're savvy, they just launch into a business. Wow, we should start a construction company. Or a bunch of architects get together, or a bunch of dentists get together and start a dental practice. So they're not going to pay you, database designer to, give them a new ER diagram and make a nice database to store all the information. They'll just tell their front staff, just open up Excel and then name a spreadsheet, clients, and start putting people's names and numbers. That is really what this seems like. In other words, a spreadsheet, which is really cell, right, is not a database at all. Visually, it looks like a table because it has column names and has rows, So that is a superficial reason why many people start using, an Excel spreadsheet as a database. But spreadsheets are quite horrible for database purposes. They have absolutely no query capabilities. I mean, there's many, many more things wrong with them. But then, I'm going to tell you some of them. The main thing is this, right? All these bullet items, these 4 bullet items. One of them is the project number attribute could be used as a primary key along with project name, but it contains nulls. So suppose you ask in here, what can be a primary key or what combination can be a primary key? These things are all filled. All of these are filled. There's no cells that are empty. But here, there are empty cells, literally empty cells. We don't want to just type 15 Evergreen over and over and over and over again. So we're lazy. So we leave this whole block empty, knowing that these rows, like William, Smithfield programmer, should be right here. We cannot copy and paste this row at the bottom. If you do, then something bad happened. You're charging the wrong customer the money that this person put in for the hours, right? In other words, there's an implicit assumption that spaces means all of these belong together like a block. That's right there a very bad idea. You introduce some kind of a positional dependency, okay? A different way of saying that is, because all of these columns are not filled, there's holes in them, they literally cannot be a primary key. Because if you cut this row and you put it over here and you ask somebody, what project is that the person worked on? You have no idea, okay, because it's blank. So there's so much information that you're assuming that hopefully nobody would scramble all of this. Like, for God's sake, don't sort any of this and save it, okay? You'll completely lose all the information. It's very bad. Likewise, data inconsistencies if name or title is misspelled. So you would hopefully copy and paste something, right? But then suppose somebody's name changes and Alice gets married or something. Then you want to change Alice's last name. So now she's Alice K. Smith. And Smith is a pretty simple name. So then rather than do a search and replace, the front staff just says, I'll just copy and I'll just click here and correct it. SMITH. And then now, they're in a hurry, say SMITJ. Okay, J is next stage. And then that becomes a new person. So you introduce like an anomaly. Then if you say, how much money did we make from Alice Johnson, that query would now not catch, this misspelled name. So now you're losing money or you're getting incorrect information because you manually try to change names. And why did you have to even do that? Because Alice's name is in more than one place. This wouldn't happen if Alice's name was only in one place and then it pointed to everybody else that needs her name. And you change in one place, like a function call. You make a bug fix in the function call. All the calls that actually call that function, the thousands of places, they'll all benefit from the bug fix. If you don't have a function call, you're on your own. It's the same idea. This, in other words, is called redundancy. Redundancy means information is unnecessarily repeating. There's no reason why any of these names should be multiplied at all, okay? Employee number, fine, okay? That's just an ID. But we should not be having those names and numbers together. It's complete waste. It's a waste of space. It has the possibility of introducing errors. All right, so that is what this was. Redundancies exist could lead to insertion anomalies. Yeah, so if a new employee joins this construction company and the new employee is the star architect, but the other projects are already in progress, so we don't want to charge those other projects for this new architect. The architect has no work to do yet. We hope to put them on a future project. Right now, there's no way to do that. What you have to do is, basically put them on because wherever you put them, there's going to be a hole there, right? If you put the new employee at the very end, then it seems like they're part of Starflight. And if they have a job title and everything, then hopefully this number is 0. Otherwise, the query would even take them into account. It looks ugly to put a new employee under some project, even though they have no project. Won't be able to tell to get all the places her name is all this. Yeah, you can. This information is very small. Imagine this is the Amazon customer table where you've bought like 100 things, and then somebody's trying to change your name in all the 100 places. Then it's a problem. So this is a very simple toy example. The only best thing to do is search and replace. Literally do a search and then just do a replace, okay? So then if that is possible, then you can avoid what I'm saying. But even then it is a bad idea because you're wasting table space. That's really the true answer. And it's a bad design. Okay, so you have to assign somebody to a fake project or maybe some existing real project. And then update anomalies. So this is the one that I mentioned. If you change something somewhere, suppose, Joan gets a promotion now, she's senior electrical engineer. Then if you forget to say the word senior somewhere else and say this number changes, then somewhere else you did not change the number, then you're charging that project less money than you should be charging. She got a promotion, but then you forgot to make the number go up. So this construction company literally will lose money because you did not update the information in every place. Then to back up, the information should not be in many places. So there's your problem right there. So that is called update anomaly, when you have to change something and you don't do it right. Deletion anomaly can happen when, suppose a project is down to only one employee, because gradually people start leaving the project to go somewhere else. The project is winding down. So then suppose that one employee that is in that project, still working on it, decides to join a different construction company. Then you think, wow, I'll take this person off the table because they're not my employee anymore. But if you delete them, the whole row is gone. It means the project information is also gone, because that is the only person that had that whole project going. So now when they're gone, the project name is gone. That is also, like a loss of information. Wow, we don't even know how many projects we worked on last month because we deleted the names. See, these are weird, contrived, meaning they're made up fake examples, but they are true in the real world. So deletion is a problem, insertion might be a problem, and definitely update is a problem. If all else, if you don't accept all of that, you cannot argue with this. You're just wasting all the space. So we should not be storing this information everywhere. Okay, that should only be in one place. The fact that it's a database designer must decide that they're being charged $105 an hour. Likewise, somebody's employee ID must give us the name. Even the project number should be able to tell us what the project name is. So you see slowly where we're going with this, okay? The way to get rid of all the problems is make new little tables and then put information only once. And repeat information only when you really need to. I'll give you the bottom line, okay? In this whole table, the only information really that needs to be repeated is project number, employee number, how many hours they worked on a project. 3 columns, okay? And yes, the employee number would repeat because they could work on multiple projects. But that is the only time, that's the only column in which you're allowed to have multiple, numbers. Otherwise, these can all be different and those definitely are different. And you can have many entries, by the way, meaning every time 15103, 15101. So keep the 15 column, have 15s, have 18s, have 22s, have 25s. Have the employee number, just leave it alone, leave it alone. Basically, throw everything in the middle away. That's what we're going to do. Okay, so it's going to become a 3-column table and all the other columns go somewhere else. That's what's going to happen. So when you have holes like this, these are called repeating groups. A group is when you only put information up one time and you're too lazy to copy and paste it. It looks bad. So you leave it blank. That is called a repeating group. So we have repeating groups. When you have repeating groups, we call it the zero normal form. This is not normalized in any way. This is legally not even a table is what we're saying. Because every column should have something, okay? This almost looks like it's null. It looks like we don't even know what, project this person is working on. But that's not true. We know it is 15. We know it is evergreen. We didn't put it there. So that kind of a thing is called a zero normal form. It's really not even a table. To make it a table, you should at least fill in the blanks. When you do that, you're going to get the first normal form. Okay, so normalization's goal is to ensure that each table is well formed. That means full functional dependency. Each table represents a single subject. Here we have too many confusing things going on. We're storing project information, we're storing employee information, we're storing job category information. So we shouldn't do that. Again, in a class definition for a piece of software, a class should only do one thing. So when a class is doing too many things, break it up into multiple classes and then compose them, or connect them to send messages to each other. All right, so each table should only have one thing in it, one kind of thing in it. And then this notion of repetition. So you should not have anybody's name, any $105 per hour, or even project name repeated over and over unnecessarily. Repeat it when it's necessary. Otherwise, don't. All non-prime attributes, things that are not primary keys, things that should be looked up, should be dependent only wholly on nothing but, again, the key, the whole key, and nothing but the key. So help me God. That's what this is, okay? So our tables should be such that if you have a composite primary key with 2 columns, both those columns should be needed. There should be no column here for which only one of them is enough to look up. Again, things I've said before, but now you see it from a normalization perspective. And then, so if you do that, then all the tables are going to look totally fine. If you make a change, it'll only happen in one place and everything is fixed. All the problems we mentioned in the previous slide would be fixed. All right, so then here's just a bird's eye view of what those normal forms are. The first normal form is, it's a table, no repeating groups. It means you literally just fill in the blanks, okay? So I can go to the thing that I showed you and put 15, 15, 15 all in the holes and write evergreen, evergreen, evergreen. But that alone is not enough. You have to do one more extra little thing. You need to look there and find out what could be a primary key. So after you fill in the blanks, then what could you call a primary key? And my answer would be project number, employee number. That combination would be a primary key. Because you see, that would be unique, okay? Those 2 columns would be unique, like 25, 107. There's no other 25, 107. So you need to identify that. Because then in terms of that composite primary key, we'll start looking at all these other columns, every other column that is not a primary key, and say, do you belong in this table? Do you belong in this table? Do you belong? Do you belong? Do you belong? And if the answer is no, we throw it out. So the normalization is a perfectly clear idea now. All right, so therefore the first normal form is all the cells filled, no holes, and then you know what the primary key is. Then you go from 1 to 2. 1 to 2 means in 1 there was something called partial dependency. That means certain columns, such as the employee's name, you did not need the composite. You did not need project number, comma, employee number. You only needed employee number. So if only a part of the key is needed to look up someone's name, then that's called a partial dependency. If you throw all such cases out, take it out of the table, then you will get second normal form. The third normal form is very interesting to go from second to third. The third normal form happens when there are some columns that are not even a primary key at all, not a part of a primary key, not a full primary key. They're not keys at all. They're normal tables, normal columns, but they act like a primary key, okay? You have to get rid of them. So once again, what I said about employee's name is the employee name only needs a part of the primary key. Likewise, the project name only needs a part of the primary key, only needs the project. So those are called partial dependencies. Likewise, okay, so that's a partial. But then look at this. This, if you tell me what this is, that can determine how much money comes with the job title. So this column right here is a weird column. It is not a primary key. It is not a part of a primary key. It is not a key at all. So when that determines something, you have a situation like that. You have to take that out. That is now called a transitive dependency. It's transitive because, again, if you give me the employee number, then I can go and look up what job they have. And then because that job, what they have tells me what money they're making, it's as if I could have done it myself, but I'm hopping, I'm jumping. Okay. So that extra thing in the middle is being like weird. So we got to get rid of that. So then that's called a tertiary dependency. It's called a transitive dependency. So when you get rid of that as well, then you will have full, normalization. Pretty much we can skip the rest of the slide because that's all it is. So after you've taken those transitive dependencies out, like, job category, space, charge per hour, then we have full third normal form. It's really straightforward, right? All right, so the process then is what I told you. All the tables should be 3, not less than 3. And then higher normal forms don't usually occur. And then if you, still do 4 or 5, it'll become really, really slow. If the job's hour rate change, the reference would be pointing to value. Yeah, you're absolutely right. So you can maintain history. This might be one reason why you would not normalize. If you want to maintain historical, information like that, then you would not normalize. That is correct. What you're saying is absolutely correct. Yeah. Okay. So in the very last slides, actually, that's one of the things we'll mention. For historic reasons, if you want to, have somebody who has 2 months, both like old and new, then that column should not be removed. In other words, a cell is a cell is a cell. Okay, a cell can only have one column. But the way we have it, the same job, like database designer, can have multiple salaries. Say these are old salaries, at the top of the spreadsheet is old dates. Then when you get new dates, the person got a promotion. Then the way we have it, you can put a different number. But if you normalize it, then that luxury that we have would go away. You can maintain normalized, right? I see we can maintain and normalize to do right with dates you and normalize. Yeah, I mean, usually, the whole denormalizing is done for history reasons. You can find other ways to do it, by the way. So what Garima is saying is actually very true. You can have a separate table where you can make those entries, okay? You can actually, like maintain more than one piece of info if you want. Okay? Several design ways to fix it, you guys. But I want to show you the proper way, the main thing, okay? And then we can talk about other things. So work on one table at a time. This just means entity. So one table at a time, carefully look at all the columns and make sure that only primary keys, full primary keys, determine everything else. Otherwise, normalize, break it down. Okay, that's all. So only the primary key, the whole primary key, nothing but the primary key, should act as a determinant. How do you do it? You start analyzing the columns. So then it's about functional dependence, which I'll fully skip. We don't need this notion of full functional dependence, by the way. So functional dependence means only keys decide, non-key attributes. Like your student ID can decide everything about you. Full functional dependence is only for composite keys. When you have more than one column that is a composite key, then all those columns are required. There are no wasted columns. Or the other way around. You should not have just one of those columns, go and decide something else. Again, employee number, an employee name, that's an example of partial functional dependence. We don't want that. All right, so that's that. And then these are the two things we're trying to get rid of. When you go from 1 to 2, we get rid of this. When you go from 2 to 3, oh, I have a typo there. Sorry about that. I'll fix it. All right. So when you go from 2 to 3, if this exists, then you go from 2 to 3. If this doesn't exist, then 2 and 3 are the same. Okay. In fact, if none of these exist in your table at all to start with, then 1, 2, and 3 are all the same. There's nothing to do. Okay, how do you go from 1 to 2? Partial dependency means a functional dependence in which a determinant is only a part of the primary key. Again, if the primary key in our example was project number, comma, employee number, we have a situation when the employee number alone is able to give us the employee's name. So we have partial dependency. Okay. Transitive dependency means something that is not even a key at all, like job title is telling us how many dollars per hour the person makes. Then if you have that, it's called transitive dependency. Because we don't need that at all. That should be in a separate table. We should promote that and make it its own table where the job description, the title, would be the primary key. And then how much dollars per hour they make would be the thing that you look up. The number cannot be the primary key because many jobs can have the same rate per hour, right? Therefore, only the job title, which is hopefully unique, should be the primary key. Okay, so we're going to see all that. Partial is pretty simple, okay? So if AB is primary key, partial means A alone decides something, like the project number decides project name, or employee number decides an employee's name. So those are partial. Again, same thing, right? So, like in this AB example. So if A and B together decide C and D, you think. But if you examine closely, well, wow, I actually don't need A. B alone can tell me what C is. Then you have partial dependency. Okay, I've shown you all this, okay, so we don't need to spend time reading all this. Somebody switched. Okay, is it possible to have wow, that's a great question. See, that's one of the best questions. Before that, why doesn't the employee number imply? It could and it should. Yes, that's one of the things we'll actually fix. But Shreya had a very cool question, okay? Can you have a transitive dependency with no partials? You can think about it, okay? Loosely speaking, the answer would be yes, right? Because they're two entirely different things. Like in this case, suppose we go and fix everything so that, the primary keys decide everything. Then you can ask yourself, then would that column, which is the job title column, even be in the table? So I'll tempt you by saying, it seems like it is reasonable. But on careful analysis, you will actually find that this is not the case, meaning you cannot have transitive dependency without partial. Because when you clean up partial, the cleaning up will also get rid of the transitive. They're hierarchical, okay? Like one follows another. So you cannot go from 1 to 3. You shouldn't need to go from 1 to 3 without going from 1 to 2. That's basically what you're asking, okay? Yeah. So that is not possible in real life. But think about why, okay? In fact, use our example to think about why. All right, so transitive is easy. Transitive means, again, if I can, determine somebody, like say my employee number can tell me the job title, but the job title can then tell me how many dollars per hour. But I can also directly go and find dollars per hour myself. Then I have the situation of transitive. Like to get to Z, I can do it myself, but now I'm going through Y to get to Z. So that's like one level of indirection. We call it transitivity, transitive relation, okay? Like A implies B, B implies C. Therefore, you can conclude A implies C. It's that. Therefore, again, a non-prime, like a standard column, is acting like it's a primary key. Therefore, the solution is to make it a primary key, make it its own table. Okay, moving on though, okay, this is actually going like really fast and nice. 0 to 1 is pretty simple. Just fill in the blanks and identify what the primary key, should be for all the upcoming analysis from 1 to 2, 2 to 3. So fill in the blanks and then also identify PK. Our PK is very simple. Okay, that is the only thing in the whole sheet that is unique. What project, what employee, and then finally how many hours the work should be the thing you can look up. Because you cannot store that information any other way, okay? Think about it. So you at least need those 3 columns to properly bill everybody. Who worked on what project for how long? Okay, so simple. And then the rest can all just follow. How much money you make can follow from it. Therefore, that is the only primary key that is reasonable. Nothing else is reasonable. You cannot have somebody's name as the primary key because that could repeat, right? And the project name also cannot be the primary key because you might misname, 2 projects with the same name. You like the word evergreen, we call everything evergreen, which here you could do as long as each evergreen is a different number, 1, 2, 3, 4. Okay, so therefore these 2 numbers combination is what we'll use as a primary key. There's no doubt there. All right, so then we'll do something very cool. We'll draw this neat, simple diagram. It's in the next. Okay, to have the duplicates, or it doesn't matter. Yeah, when you fill in the blanks, you will have duplicates, like 12, 12, 12, 12. And that is why we call it a bad design, because you want to come up with new tables that don't have the duplicates. Yeah, you definitely will have duplicates. And there's nothing wrong with it. It's better than what we had before. Then you can cut any row and paste it anywhere in the table, because all the information will go with it. You don't make any assumptions. But you're wasting too much space to store all the repeating information. So that's the answer. All right. So then you take those columns, and what if you could color the columns, okay? What if you could color the columns in 2 different ways? The columns that are primary key combination, you color them some color, probably green, okay, just color it green. And then the rest you can color in a different color. Why not just do it? And so then you can start drawing all these arrows, okay? That's basically what we're gonna do. Okay, so go here, 0, 7, okay, why not? I'll put it up here, okay? Okay, so we can actually, so I'll tell you what I mean. Yeah, maybe we can form, yeah, that's what we're gonna do actually, good. So Rengapriya is like looking ahead. What we are actually going to do is exactly that. We will, wait, sorry. I think there's a file dialog that I'm not seeing, okay? What happened to my little bamboo? I want to drop that image in here so I can actually show you guys. So I'm going to try one more time, okay? So bear with me for a second. Interesting. Yeah, we'll show the chat with the screen recording. Actually, somebody said try and put it aside. Yeah, so I'll put it aside. Okay, well, this comes up. Wow. That poor Bamboo task is maxing out the CPU. I have no idea what happened. I was just trying to load the image so I can, show it to you. So the idea is to color the primary keys separately, and then that way it's visually clear in what we're trying to do, okay? And then we'll draw cool arrows. The arrows are what will tell us what is wrong with the whole picture. But now I want the task manager to come up. We're like frozen for a little bit, so sorry. Weird. PC, right? Microsoft. If things go like horribly bad, I might actually log out and log back in, but hopefully not. Yeah, I know. Don't even get me started. I have a love-hate relationship with Microsoft. Okay, on the one hand, I put up with them. I had them for a long, long time. I had Macs like a long time ago. But PCs are more practical in terms of the hardware that you get for your money and all the drivers and all the devices and software definitely. I run like hundreds of different things. Max seems like a communist country. Okay, so then here it is, finally. Okay, so this is what I was saying. Suppose you go with that color, right? Just go with that color. So then you make the project number column a certain color. So you color it like that, project number. And then employee number column, you color a certain color. Because when somebody looks at that instantly, even if they're not together, that is your primary key. So we know that. And then everybody else, you can color somebody some other different way. We already have this, so I should just accept it. So project name, employee name, job class, charge hour, this. And then we'll just draw this diagram to say, this combination, right, is going to determine that. It's going to determine that. It's going to determine everything else, really, because that is the job of the primary key, okay? This is what you want. You want this. But then you look at this and you say, wow, that's not quite true that the combination is needed for this. You have this situation where employee number alone can give me, this way. Employee number alone can give me the employee's name, right? Like this. Employee number alone can give me employee's name. Likewise, project number alone can give me project name. Employee's number alone can give me the job class. This is what a different student was asking. And then job class can give me charge per hour. The only thing that you really need is this one. So the only thing you really need the combination. In other words, this is the only good column to have. All the other columns are all being weird because there's a partial dependency, partial dependency, partial dependency, transitive dependency. Okay, so partial, 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 and transitive. We're going to get rid of all of these. So we'll end up with new tables, okay? And then all these problems go away. So that is the idea of this. It's very simple. Mac, Macs and PCs, Mac Master Race, exactly. Well, when Macs first came out, in China, they made a knockoff called the Pineapple. There was another thing for Apple. It was called the Banana, okay? And then Apple sued the heck out of all of them and shut them down. It's interesting. And then for a while, Apple officially licensed their, the hardware design to a company called Radius that made cool monitors. And then Radius made so much money selling, alternate Macs. Apple got jealous and said, give us your license back. No more license for you. They took it back. Apple's a very interesting company. Okay, so then they should skip all this, okay? So then the point is, how do you make the diagram, okay? The diagram is very easy to make. What you do is it depicts all the dependencies, helps get an overview, and then you would not miss anything. Then you think, what is the point of those arrows that look pretty silly? But imagine, 80 columns. Then I think the arrows make a lot of sense. You can carefully make sure you miss nothing. And here's what you do. I already showed this to you. So tell yourself top good, bottom bad. Okay. So in here, the combination is determining charge per hours. That's the only good design. Even though you want the rest, ideally you want both of them to give you the project name. But in reality, that is not true because this is canceled by this. There's a partial dependency. Likewise, you want that combination to give you the employee's name, that combination employee's name. But this is canceled by a partial dependency. So this is bad. Likewise, this is also bad. So that error goes away. And then you could directly, look up the charge per hour, but then transitive dependencies, I can do it too. Therefore, that column is being bad. So these are all partial dependencies, transitive. So we want to get rid of all of them, okay? And therefore, in this table, the only thing worth having is really number of hours the employee worked. That's what I told you. So in this thing, the only thing really worth having is 3 columns: project number, project name, how many hours they worked on that project. And this is how you, by the way, write them. Suppose you have no place to draw a diagram, you're posting on some ASCII, you're texting somebody, then this is what you would do. You would just say, 1NF, and then just simply list like all the columns. And then you say partial dependencies. So what are the partial dependencies? What decides what? Project number alone decides project name. Employee number alone decides employee name, and job class and charge per hour. So all three. And then this is also additionally deciding charge per hour, and it's not even green. And then you call that transitive dependency. So then the goal of normalization is to get rid of all of them. When you go from 1 to 2, these will be gone. This still remains in 2. When you go from 2 to 3, this will be gone. Easy, right? All right, so what is in here I explained. So I'm going to skip it. All right, so again, conversion to first is all the keys, no repeating groups. I've said this before, okay? Yeah, okay. So 0 to 1 is pretty simple. 1 to 2 is when you get rid of all those partials, such as how do you make sure that in your new tables, a partial dependency from project number to project name is not there. How are we going to do it? We're going to make new tables, okay? This is the secret to everything. Keep making new tables. So every time there's a partial dependency, make a new table for the partial dependency. And in that new table, there is no partial dependency. And come back to your original table and delete that column. Delete the column that needed only partial dependency. In other words, make a new thing that says project number, project name, and go back to your main table, delete the project name. Make a new table that says employee number, employee name, and go back to the main table, delete employee name. For that matter, other things, the employee's job title. So your main table that we start with is going to become really thin. That's it. Okay, so table is 2NF when it's 1NF and includes no partial dependencies. Okay, so it's time to show you all of that. It's really very simple, okay? Like this. So see now there are 3 total tables. We only had 1 table, but now we have 3 tables. 1 table, like I said, if you give me the project number 12, I can tell you evergreen. That way, every new project only goes in this 1 table. That name is nowhere else, okay? So I have a typo in the project name. I fix it here. Suppose it's evergreen. I want to change it to Everglades. Just change it, and it'll all change. Likewise, employee number is a big one in the sense I can decide 3 things because of the employee number. I can decide the employee's name, and then what job category they have, and then also how much money they're making. You can look at that and say, wow, we can have a new table for this. We'll wait till the next step, okay? But right now, it is true that I can look that up, okay? So in that sense, this is second normal form. And then that combination, this is the only thing we keep in the original table because it's the only information you needed in the first place, okay? I told you that in the beginning. So this is your second normal form. It has 3 tables, and this table looks good. This table looks good. You still analyze each table and say, is there a partial? Is there a partial? Is there a partial? Is there a transitive? Yes, there is. So 2 is not the same as 3. To go from 2 to 3, get rid of this. Make a new table just for this, where this will now become olive color. It'll become a primary key. It's very simple, right? So that's it. So 2 to 3, remove the transitive. Remove the non-prime key, which was the project job title. Masquerades means hides. So it is hiding as a primary key when it's not really a primary key. In other words, it is not the job of this to tell you what this is, but it's acting like it's its job. Then we'll cut it out and make a new table for it. All right. So therefore, same thing, just make a new relation, meaning make a new table for it. So in the third normal form, take any transitive dependency, make a new table for it, and then go back in the main table and just delete it. That's it. Therefore, 3NF is also in 2NF, and it's also in 1NF. It's very easy. So then 2 to 3. Now, after 3, so this is what you're looking at. The result is the third normal form. You have now 4 tables total, and all the tables look perfect. There's nothing more to do, really. So just look at it. If you give me the project number, I can find the project name. That's great. If you give me somebody's employee ID, I can tell you what the name is and what job description they have, which is good. But then if you ask me, but tell me, how much money, the description, I can go to a separate table, so that's the same as that. But now it's a primary key, and then I can tell you how much money it makes. Supposing that job, the company decides to charge everybody more money for the job. Suppose there's a data science, data scientist job, and then the company used to charge the clients $100 an hour. Now, hey, well, let's charge $150 an hour. You only need to make the change from 100 to 150 in one place. Next time you run the report, it'll correctly do it everywhere, which is neat, right? Again, like a pointer, they're all like function calls or pointers. Okay, so this is the only place where that connection is stored. The actual number is stored. And then finally, this is the one we always had, from the start, which is what project number, what employee, what assigned hours. Okay, so employee, employee B, what. That's really all. So just simply, find out how much money we're making. Cool, right? Are these still called partial dependencies? No, there are no more partial dependencies, okay? They're all full dependencies only. Partial means when you have more than one primary key column, you should be able to look up something based on only a partial information. If you have the situation, it is called a partial dependency. Here, only a single column, there's no notion of partial dependency. You need that column to look something up. So no partial, no partial, no partial. Most importantly, here, no partial. All right? Yeah, so partials are gone. Partials go away when you go from 1 to 2, okay? So again, what is meant by a partial is what we had when we started. When we started, even though you think that this is the primary key, a part of the primary key, meaning only one of the two information or one of the piece of information alone seems to be enough to look up the project name. So this is the partial dependency. And this seems like bad design, okay? In other words, this is why things repeat. So we should take it out. And then the partial dependency is gone. Likewise, the employee name repeats over and over and over because we should actually have that in a separate table. So these were the partial dependencies we got rid of. We got rid of 4 partial dependencies, 1, and then 1, 2, 3. We got rid of this partial dependency with 1 new table. We got rid of all 3 of these with a second new table. And then we got rid of this with a third new table. And then you had the original table. So 4 tables total, all right? Well, by the way, you can search, for more examples of these. So just make sure you understand the process. And it's very simple, but at least try to do more than one if you want, just to get the exercise, okay? That diagram is called a dependency diagram with the arrows at the top and the bottom, dependency diagram. So in an interview, somebody might, give you like a bunch of columns and say, draw the dependency diagram. They want to know how well you understood this. Okay, so then one more time, this is the 3NF. This is our end result. What is the most? 3NF, absolutely 3NF. Because 3NF strikes a practical balance between what looks like clean design and overdoing it. So 3NF is where you start. You can actually do very interesting things, transitive dependencies when none of the columns is a primary key in the original table. Yeah, none of the non-primary columns is a primary key in the original table. Exactly. So, the job description is not a primary key at all in the original table. But in the original table, it helped us look up how much money somebody is making. See? In this table, if you ignore everything that I told you and say what is the absolute minimum that you need to keep as a primary key, then the answer is project number, employee number. Then if you say, if I have that, then what is the other thing that I must have here? It is how many hours some employee worked on a certain project. That 3 pieces of information cannot be anywhere else, okay? So therefore, some project, some employee, how many hours? That is the minimum we need. Everything else is a waste. And this is especially a waste because this is like in a non-prime column. It is just simply any other column, meaning it is there because employee name, employee number can decide what that is. But usually job titles come with figures. So in that sense, it seems like it should be a primary key, but it's not a primary key or even a part of a primary key. Here, a part of a primary key is acting like a primary key. Here, a part of a primary key seems to be enough. But this one is not prime in any sense at all. When you have that, that is called a transitive relationship. Okay, so these are good questions. I think everybody's answering and understanding the whole deal. And like I said, it's so easy. You know that you are done when every single table that you have, all the 4 tables, have no partials, no transitives. Again, in a 2-column table, there's absolutely no notion of partial because you need that key. So these are clearly 100% okay. Same with here, only 1 primary key. So if you give me that, I can look these up. Here, there might be a partial, like there might be a situation where only employee number can tell me, how many, hours they worked on. But that doesn't make any sense because you need the employee number and also the project to know how many hours they worked on that project, meaning there's no partial here. And there's no transitivity when you only have 1 column that you're looking up, okay? So all the problems went away. Employee name, job class is transitive. Employee name, well, the whole idea is transitive. Yeah, exactly, correct. Employee name, dollars per hour is transitive. Okay, so like this, back here. In other words, you can get to how many dollars, per hour in 2 different ways. On the one hand, from the employee number, I can look up their title. Okay, and the title can then tell me. Or on the other hand, I can directly look it up myself. Right now I have both the situations, right? So when I can get to an information in two different ways, then that is transitive. And then we get rid of it by making a separate column just for this little part. And then use the employee number to decide just this little part. And that part can then tell me that part. Cool. Okay, so back to third normal form. And then we finish up by cleaning up our design. Okay, so at this point, if somebody hired you to do this, right? You can walk away saying, wow, this table is in a much better situation than it ever was. You'll have no anomalies whatsoever. You can only put things in one place and good luck, have fun. You could go away. But then you want to do better than this. You go in a park and you have a picnic. You want to leave the park cleaner than you found it. Like somebody else left a little piece of trash. You should pick it up. Okay, so that is what we're going to do. Exactly. So, like CG says, the problem is when you try to find out information, you now have to jump between tables. And that's going to be slower. DBA won't kick your ass. No, customers will actually kick your ass. So it's about joins, right? That is why you don't normalize. You actually glue some of these tables back. Yeah, that's denormalizing. Correct. Okay, so you can do a better job, meaning then what you are going to leave behind by renaming some of the primary keys. Okay, so maybe the job description should not even be the job title. Like database designer should not even be like a primary key. I should make some other blind ID 1, 2, 3, 4, and I should call it job code. That's even nicer, right? So likewise, what is charge hour? Like, what does that even mean? You should say job charge hour. Maybe you rename the column. Okay, an employee name. So why should you have Alice K. Johnson? Maybe you should have first name, middle name, last name. So we can actually clean up the columns a little bit. So these are all nice cosmetic changes. Okay. Likewise, in the employee table, why not put the hire date? For that matter, why not put the birthday? Right? You can have extra columns. And then you can even have new relationships. So maybe if you wanted the project table, you only had project number, project name. But maybe you can have a project manager. You can have an employee number. And if you put a number there, that means that person managed the whole project. You can give them some award at the end of the year. So we can actually have new columns we can add, okay? So these are all things we're going to do pretty soon. And then this is the one that somebody said, so what if, you want to maintain like over time, you want to do basically, data mining. Then you want to keep like all the information, even though the information is going to be duplicating like project numbers. Then for that reason, you justify your reason and then have redundant duplication of data. But then the purpose is I want to do, data analysis. So that those are all the things we're going to do, okay? And then we'll also do some derived attributes, like some things we can just calculate, such as, dollars per hour times how many hours they worked on. That can tell you how much money to charge the customer. But supposing you do that constantly, like every day you wonder about how much money we're making, that multiplication of, $100 per hour times, 10 hours is $1,000. That multiplication takes time. So I can pre-calculate that multiplication and store and waste like a column, but then my query is going to run really fast. That's what this is, okay? So you can maybe have a column of redundant information, at the convenience of running your query really fast. So these are all design decisions. There's no one right answer. All right. So therefore, the primary keys again, atomicity, granularity. This is the same as what I said here. So how can we make this even better? That's what this is. I'm going to show it to you. When you make those extra changes, then all the things I talked about are all here. Project number, project name alone is enough. Okay, this should be enough. But now we can also additionally have a project manager and then have employees' numbers. This way you can do some extra analysis. Like who was the manager who made the most money for us last year? So now you can calculate, because previously you never kept that information anywhere else. But now at that column is going to help you do it. Because for every employee, find out what project and go and calculate all the money the project brought and then sort it. Then you will know who the best employee is, the best manager is. So that column we added, okay? Likewise, we can also rename this charge to job charge hour. That's a little bit more meaningful than charge hour. So that way you'll know. Oh yeah, sorry. This is like how much money you're making, right? So every job title, like database designer, when you say charge hour, what does that mean? I would even call it hourly rate, okay? I would even rename this and call it hourly rate. That's what the whole world calls it. So feel free to rename the columns to make more sense. And then do this. So why even have this as primary key? Make a brand new primary key called job code. This is what real companies do. They have every job that they advertise, they have actually a secret number for it. So that number is the primary key, not the job name, because the names can be quite long, right? So usually use blind IDs. So this is the extra thing that we did. And then you make that be able to look up this and look up this. So then the employee, next I'm going to show you the employee table, will only have the job code. So for every employee, what is the job code? I still remember that I saw a query in internship that is taken to you. Yeah. Interesting. Yeah, the more data you have, those things can take a long, long time. You're literally just sitting there. You think your database crashed. Okay, so this one I'm going to put up here. The employee. Oh, this is very cool, by the way. This is the historic data. Okay, so assignment number. Okay, so assignment number means every time somebody works on something, I'm going to have a new column for it. I'm going to keep 1, 2, 3, 4. How many little, individual projects and assignments we ever had? It's going to be a long bunch of them. And this can have lots of repetition. So when was that assignment made? Like, when did you start? When did a certain employee start on a certain project? You can even have end date, by the way. So when did they finish? And then this is the main thing you need, So how much money, how much time you put in. As a minimum, you only need this. You only need this, this, and this. But now we add more information, especially this, just for redundancy, meaning for calculation speed purposes, we put back this number. Although we can easily look this number up from starting from here and finding out what the job code is and what the job description is, right? So we waste information here. This is repeated. And even worse, we multiply this and waste even more column. But the reason to do all of this is it's trivial to add it. And then every second you're going to know how much money you're making. So we make a design decision to purposely waste space, and computation to make all of this. But otherwise, design-wise, we don't need this, okay? And then we also document it. We just say, by the way, from these you can get that. So these two together is going to give you that. But then you see clearly, that's not even a primary key. There's some kind of transitivity going on. So that's enough. That's okay. You justify it by saying the query runs really fast if I do it this way. So then you document it. Somebody says, why did they do that? Well, because I thought you want your answer really fast. Okay, so then one more thing. Therefore, in the employee number, then like I said, in the employee table, what can you do? You can add some more information about the employee. You can have the name broken up into last name and first name initial. And then the hire date, you can have some extra information. And previously we used to say database designer, but now we can put in the blind ID because the ID can tell us database designer $100 an hour. So we clean this part up, added this. So you're just making your design nicer, right? Because you take pride in a good design that nobody can criticize. That's it. So normalization was trivial, right? In a way, like, wow, this makes so much sense. So before we did all the extra stuff, it was so easy. Get rid of transitivity, get rid of partiality, and then you're done. Fill in the blanks to go from 0 to 1. And then there might be reasons which came up in the chat so many times, including that one. So why do you want to, denormalize? Because normalizing might make your queries run very slow. Because what used to be in one place is now literally in multiple places. And all the things that I told you, this is a very good relational database site called essentialsql.com. So then if you want like a little bit more explanation, it's the exact same thing. Okay, so like this, it's all about reducing duplicate data. Okay, like you don't want to have duplication happen. Wow. Okay. It doesn't matter. Okay. You can get back to the main page. Just go read that. So somewhere they're hiding it. All right, maybe there. Okay, so like that, right? 3 normal forms and all this, and then they tell you what a table is. Just basically a lot of words. And then they use this example, slightly different example. And you can see the problems, okay? Again, same thing what I showed you before. We don't need to repeat things. Okay. And then you start to go from 1 to 2 and 2 to 3, and then you'll have more tables after that. Okay. So all of this, what will happen if something changes, or if somebody leaves, they take more information with them. All right. So first normal form, everything is atomic values, meaning no holes, okay? And then second normal form means all the partials are gone. So everybody depends on the full primary key. But there could be transitivities. So that means non-prime columns, are not any longer used to look stuff up. Everybody's being looked up only by primary keys, only. That's third normal form. Hey, cool. We are done. What about this? So denormalizing is when you go backwards, because number of tables expand when tables are decomposed to form normalization. So decompose means break, right? So every time you decompose, something into something else and what, then you have more and more tables. They look clean, but then you have to join them. So joining tables takes time, and this reduces system speed. Things are not responsive anymore. Your app does not update. Then the user complains. So you denormalize. It means you literally go back from 3NF, you go back to 2NF, you leave a transitivity in there. Like I showed you here, right? This is an example of, leaving a transitivity on purpose. Like, right, where's that? There was one place where we had the diagram, it's like here. that one. So that's on purpose. This is all like not normalized. But then you have a design, note that says we're doing it this way because this number is now pretty easy to add up. In SQL, there's a command called sum. So you say sum parentheses and then the column name, and instantly you'll get the total. So that might be faster than having to do multiplications from multiple tables even. So therefore you denormalize on purpose. Okay, that's all. All right. So therefore, what did we say? Like 29. Number of tables reduces system speed, therefore we do it. Again, if you denormalize, you go back to efficiency. Things are now much larger. They take more storage space. They take longer to transmit over the network. Indexing, this is actually a pain. We never talked about indexing yet. This is for a future, lecture. But indexing is much easier when everything is only in one place. Indexing is a way to actually find information even faster than not indexing. Like if you have a book and you want to look up the word SQL in every part of the book where it says the word SQL, page number, you go to the index on the back of the book because somebody pre-looked up where the word SQL occurs and they put all the page numbers. That is called indexing. So we can look up all the row IDs where something is and then pre-store it. So then that indexing becomes very hard when you have all the repeating information. Okay, this might be the really big reason about like not having denormalized. But indexing is not impossible. It is just hard. Indexing is easy when you only have separation of concerns, meaning the table is only about one thing. I can use the primary key to index that thing. But when you have too much data repetition, then I have these multiple composite weighted primary keys, and so that makes indexing harder. In other words, indexing is not as efficient as it could be. That's pretty much it. Okay, so forget the whole virtual tables. Okay, so I'll tell you this like after we do SQL, which is now. Cool. So again, overall, normalizing is a good idea, but practically speaking, it does not make too much business sense because it slows people down, and then you don't normalize. That's really all we said so far. In the real world, denormalized tables exist, but then somebody would justify it. They'll say, well, it's not that we did not know what to do. We're doing this on purpose. We're leaving it like that on purpose. And that's okay. You justify your design. Okay, so now without missing a beat, we just skip into SQL. Okay, just jump right into SQL. What happens is here, this is neat. In fact, it goes nicely with your homework. For homework 2, what you might even be told to do, I have not thought about it yet, is to use SQL, all the commands I'm going to show you, to actually make your design be a real table. So you'll have a real table. The very last slide, 68 or 68, tells you so many different ways in which you can actually do all this for real. And then your tables will become, your design will become real. So you can have like 20 customers and 3 surgeons and 4 orthodontists, and then you can find out what is happening in that dentist practice. You will write SQL to find out how much money are we making per day. What does the daily schedule look like? Okay, so that's going to be pretty neat. Therefore, pay attention. It's a fun thing to do, and SQL knowledge is damn valuable because this language that I'm showing you, it appears to only work on tables. These are all table examples, but in NoSQL, in the world of NoSQL today, there's no tables anymore, but we still keep the language. This language is so good. There's no better way to query even big data. Okay, even NoSQL database, they all have a version of SQL. So SQL knowledge is not useless at all. Relational tables, maybe we don't use as many tables as before, but the SQL language, people actually tried to throw SQL away, but then they came back to SQL because they could not replace something with better. I want to make a political joke. I'm so tempted, but I want to make it. Okay, so then 1 out of 68, SQL. Where does SQL come from? So I told you, in Ed Card's paper, right? He named all those relational operators. For example, he used the letter pi because pi is P, right? P is for projection. And then likewise, he would say S, like sigma. He used sigma, lowercase sigma, because sigma is S and S stands for select. So he made the so-called relational algebra, right? That's what all this is. And it just simply means those table operators. So if you have a closure with 8 operators, I can just simply, this like multiplication is join, right? Cartesian product. So I can just simply do any table operation with those 8 operators over and over and over again, and I'll keep getting more and more tables. It means I can combine them. So that's what all of this was. All right, so then SQL language says, okay, I'll make it for real. I'll make all that come true. So when you type all these commands into a SQL console, you run it. And then those operations that Card talked about will happen on real tables. Like in the dentist table, you can throw away the employee's birthday column if you didn't want it. You would do a project operation. I named this earlier, okay, so, but now I'm going to give you SQL examples. Again, select is the biggest thing that we ever do with all the 8. Select is all about, again, data mining, searching. So of all the 100 million Amazon customers, give me the top, give me the ones that spend more than $100,000 a year. Wow, the hell are the people that do that? I'm sure they are. But then we want to know who they are. They are our gold star customers. So you literally go through 100 million rows of people, then find out last year, who spent more than that amount. Okay, so then that is really the magic of select. Okay, select means row filtering operation. Select US. Yeah, exactly. That is very nice. Yeah, exactly. If you have a table of instructors and you want to find me, you want to find out how long I've taught at USC, other information, whatever, then you have to do that column. Yeah, I like that. Right. I can do the same thing with you guys, right? So select from CS585, where name equal to Kevin. Then I'll know your scores. That is actually what we do when we go to our spreadsheets in detail. When you search somebody by name, it does the query actually. Okay, so project is get rid of columns. I have too many columns, and so I want to cut columns away. Only give me columns that I name. And join, loosely speaking, is multiplication, but then across tables. Tables can be all completely separate. As long as some cell name, like somebody's name, is in one table, some other table, some other table. It's like I can do some cool row joining across all the tables. That's nice. I like that. And then product is just multiplication. So product will give you illegal tables, meaning it's going to give you number of rows times the number of rows. You'll have a new table with both number of rows multiplied, a number of columns added together from column A, from table A and table B. You would use it as a temporary result and then filter it and throw most of it away. Union is pretty simple. When you have columns that are compatible, I can join two tables and make a new table. Literally glue all the rows below each other. And intersect is I can take two tables that are again common and find out what are the rows, like who are all in both tables. Difference is who is in one table but not the other table. And divide is always you divide a two-column table by a one-column table. The idea is for all the columns in the one-column table, what are all the rows in the two-column table? Where all those values exist from the one-column table. Again, I give you the example of employees knowing various programming languages. So many employees, so many languages. Now I have a small list of languages. Who are the employees that speak all those languages? So simple. All right, so then Ed, IBM did not invent SQL. This was so interesting. Oracle, Larry Ellison, read that card paper and basically, hawked his house, meaning he, got a mortgage from his house, and then started Oracle Corporation. And they and others got together after a few years and made SQL. And then IBM was late to the party and said, wow, we need to do this too. Then they made a mainframe computer called DB2, a software called DB2 that ran on 360 mainframes, IBM 360. These will give a new table. We have option to say. Yeah, definitely. That's a good question. Okay. Yes, you can save those tables and make new tables. Then you wouldn't have to do all those calculations again. Very nice. That's called persisting. Okay. So you can persist tables and make new tables out of them. Sure. Very good question. Okay, I'm gonna move on and show you examples here. This is very easy, by the way. It looks like 68 slides, right? But it's actually damn straightforward. All right. So SQL is ultimately this small list of commands. It's called a programming language, right? But it does not have variable names. It does not have loops. It does not have branches. It does not have actual function calls with recursion. It does not have many things. It's not really a language for programming. It is a language for data querying. And therefore it has commands like select, project, union. There's a very small subset of them. But 100 commands is all. If you learn 5 per day, in like 20 days, you will know all of SQL. So do it, okay? I'm going to name you so many ways to learn SQL. Just do it. It's fun, actually, more than anything else. And the more you do it, the more smart you will get. It can be complicated. If it is so simple, right, the CEO would do it, right, or the secretary would do it. But it's not straightforward. The more complicated your queries become, you need somebody to think in a very certain specific way. And that is why they pay you so much money. And you will get to that level if you just think in SQL. And you can get that by just practicing over and over. So first know what the words do, and then start playing with them. So you have like all the knowledge you need for free to actually just go learn it. It's all out there. All right, so all those 100 SQL commands are broken up into 2 parts roughly. The first part, we call it the data definition language. In reality, there's no difference. You type the same SQL, okay? But then when you call it data definition language, what you're doing is you're creating empty tables for the first time. Yeah, correct. That is why they pay you the big bucks. That's correct. Okay, so empty tables, like your ER diagram right now is simply a diagram. But then at what point will the diagram become an empty table with 0 rows, but all the column names exist? Now you have an employee ID, you have the surgeon's certification, how many surgeries they performed last year. All that is ready to go, okay? But then your tables are 100% empty. To create empty tables, use DDL. Likewise, to delete tables or to add an extra column. Basically do operations on tables themselves, okay? It's the structure of the table. That is data definition language. Everything else, which is more important, is the data manipulation language. This is where you would insert like a row of data, you would delete the row of data, you would query it, you would modify it, you would combine it, you would join it, whatever. All of those is data manipulation. So less of this and much, much more of this, what you would do in real life. You might not do this for 10 years, but you do this in every 5 minutes. So non-procedural language, so like I said, it's not about looping, branching. It's not like C, C++. And SQL is a standard. It's an international standard, so it'll exist for like, forever. But different database vendors like Oracle, Microsoft, IBM, they're allowed to add extra keywords, to SQL if they want the vendor-specific extensions, or even take a word like difference, table A minus table B. Oracle might call it difference. Microsoft might call it minus, say A minus B. So those are called dialects. They're small changes in keywords. So you shouldn't freak out if somebody gave you, something in Oracle and you post that in MySQL and it doesn't work. Just look up the documentation and fix it. That's all. Okay, so it's easy. And now I can tell you the data definition command. So then these are the ones that you're used to, you're going to create tables for the first time, okay? We'll leave out the schema authorization. These are all for DBAs. I'll only tell you things that are important. And again, we have examples. So just a quick rundown. Create table creates a table for the very first time. By the way, we have examples for all of these. So I won't just read SQL to you. I'll actually show you like here, okay? You have to wait for it. There it is. So these examples will make all my abstract pictures look more real. But I want to give you the bird's eye view and tell you how simple this is, and then we can move on. SQL is always used in conjunction. Yeah, correct. So in the real world, you have things like a Java interface, you got Python, Qt, and all of that. So we'd use a version of SQL called PL SQL. They call it programming language SQL, practical SQL. But this is like SQL++, where you can have like variables, for example. You can have loops even in that, pseudo language. But then I would not really call that core SQL, so I'll skip it for now. But yes, sure, the short answer is yes. I would say Oracle, probably. Oracle is the preferred dialect. But see, I would never worry about it, okay? So forget I even brought up dialects, Or just pick Oracle because it's the oldest of them all, really. There's minor differences, honestly. It's 99% identical. Okay, so create table, make a brand new table. Some columns you can say not null when you create the table. That way the cell cannot be left empty. When you go add a row, it'll look for the cell. If the cell is empty, it'll come back and say form not accepted. This happens many times. You sign up for something and then they see email, there's a little star there. You're not going to give them the email. You say register. Come back and says, wow, one error found, go on to email. That is because somebody said that column cannot be null. Unique means like a primary key. You want to make sure that in that column, all those values are all different. We usually do a combination of unique and not null for primary keys, but we have the option of making any other column if you want to be not null, or any other column if you want to be unique. You can even make some column that is not primary key at all, should be unique. You ask somebody, pick a 5-digit number, for no reason. And then when you pick your 5-digit number, you can check against all the other 5-digit numbers and throw yours away and say guess again. And make it do that, okay? Even though it's not a primary key. But mostly that combination, unique, not null, defines primary keys. But a primary key need not be specified that way. You can use the word primary key. Any column that says primary key will be a primary key. These things have no return at all. On the shell, the return would actually be like a status. If there's an error, you will instantly know. You will like return error code. That's a good question, by the way, because secretly, these are all actually like function calls. In fact, the syntax a lot of times looks like a function call. There's a command which is a function name, parentheses, all the arguments. And so, yeah, there is a return, but usually we don't check for that, okay? All right. So foreign key is exactly what it says. Some column can become a foreign key. And default means if the user does not specify something like phone number, then make it 5551212. You can put in like default values. And check is you can perform some checks, like make sure that GPA is not negative. Those are called checks. So these are all conveniences that make sure that somebody does not put in bad data. And index is the thing that I told you, we'll do this in a future class. You can take any column and say, make it so easy to look up information based on that column. Basically, pre-switch my table and store all the information that is easily switchable, like, in the back of a book. In index. View is what the student Rangapray was asking. So view means really, when you make a query, you can call the query a view. So then you can do further queries on it. Basically, it's a table that lives only in memory. But then even better, you can say materialize the view. Materialize means make the view real. You can give a name for the view and say save the view, which is really a search, a result of a search. As a new table. and you have a brand new table. Okay, alter table is when you change the table's characteristics. Like I want to change the column name from string to integer, or I want the string value to go from 20 characters to 40 characters. So anytime you actually make a structural change to a table, that's called alter table. And then create table as, so you can copy one table and make another table out of it. Okay, that's as. Drop means delete. It's an old mainframe computing term. Drop means I don't want to, just drop it. When you argue with somebody, they keep arguing with you, just drop it. So drop means get rid of it, just delete it, go away. So drop table, drop index, drop you can drop all these things, but they're permanent unless you made backups. Okay, this is where everything is, and it's so small. Yeah. Oh wait, what happened? Can everybody else hear me, or is CG the only one? Okay, yes. Yes, what? Oh, you can hear. Okay, yes, I can hear. Thanks. Yeah. So if you say yes, that's ambiguous, right? Yes, we can hear. Okay, so look, this is so simple. Okay, I cannot tell you how simple SQL is. In a way, you already know SQL, but it seems like difficult. I would not say difficult. It seems weird. It's like a different language because you do what is called set operations in your head. Like the way you think about SQL is you don't mentally write like a loop and just say, oh, for every row, I'll check the GPA column and see if it is more than 3.9. You just tell yourself for the whole table, I'll just look up GPA. We're not used to thinking like that. We're more used to thinking, yeah, you can. Conceptually, you will know SQL by today. You're not used to thinking in terms of set operations. You're used to thinking in terms of individual rows, like an if statement, okay, and a for loop. But otherwise, you already know SQL. Because look, these operators that you use in like Java, C++, right? Exact same thing. You can say if major equals computer science. Rather than equal to, you only say one equal to. But it's not assignment, okay? So you can say if major equal to computer science like this. You can literally say if major, suppose the column is called major, you can say equal to, CS. You can literally do that. If there was a column called CS, and then if this one of the values, then that'll actually pull it up. All right, except you wouldn't say if, you would say where, okay? All right, so therefore, that's simply a comparison operator. And then this one is a not comparison, not equal to. So tell me everybody whose GPA is not equal to 4. This one is less than. Tell me everybody whose salary is less than $1 million a year. Tell me everyone whose GPA is more than 3.5. Tell me the date that is less than or equal to 1970. It means earlier than 1970. Tell me all the, something else, what is more than, greater than, equal to. So these are all standard mathematical operators. We use them for comparison. But now we compare with data in all those cells. When you have comparisons, you can have more than one comparison. You combine them with ands, ors, and nots. For example, GPA more than 3.5 and major equal to CS. That and is this and. So I can do more than one. I can have 5 or 6 or 8 even with and. Or means one or the other. So I can either have GPA more than 3.9 or major is data science. Just find all those people. So it's the opposite of and, right? Is or. It's either this or that. SAND is like a set intersection. It needs to be in set A and set B. Or it's like a set union. I'll accept either set A or set B. And not is set complement. Like tell me everybody who is not Viterbi. Okay. Then from the global set of USC students, leave out Viterbi. So these are classic programming deals, like that right there. So I have examples, but it's going to be so easy. And some of these, like between, is just simply less than something and more than something. Like tell me all the students between GPA, 2.5, 3. You're literally saying GPA less than 3 and GPA more than 3.5. So rather than type that long expression, I can, as a shortcut, just say the word between. So some of these are not even needed, okay? And likewise, in is also something or something or something or something or something. I would rather just use the in operator. So some of these are shortcuts. Like is like a string comparison, like a regular expression. That's why in our early joke that we had here, the whole like deal. So now this makes sense. So select star means give me all the column names. So suppose you're all the students, So select star, suppose everybody, is in a table called world. So the table called world has lots of information. Where someone, like, there should be likes. But the like operator is what I'm talking about. Percent U percent. That means you can have lots of words here. There should be U in the middle, and then lots of like words, letters here. So regular expression, like star, okay? So star, star. All right, yeah, exactly. Rose returned as a zero. Yes, that's where the joke comes in. All right, so like is just simply string comparison, okay? And then I already told you. So this one is the more cool of all of them in a way exists. So this means, what a query has to finish. And then if the query actually has something to give you, then the main query can run almost like a function call. Exists is like a function call. And then distinct is when you have more than one. Let's say there are many CS students, just give me one of them, right? It's all distinct. Okay. Like count them only once. I'm going to give you examples for all of these. Then, yeah, these ones are very easy as well. These ones operate only on one column. These ones don't have closure at all. These ones were not defined by code at all, but they're conveniences. In the project example for normalization, we had for every single row what employee, what project, how much money they made. So all the money, every employee, every project. I want to add all of them and say, wow, how much money did we make? Just literally add all the columns. That is simply sum parentheses, that column name. So sum is adding. Count is tell me how many rows there are, because normally you don't see the tables. Min is of all of those numbers, tell me the lowest number. Max is tell me the highest number. Average is sum divided by count. So these are trivial, right? Simple mathematical things, and they only run on floating point values on, like numbers really. So look at this, right? These look so easy. Okay. Then it's all about here. Insert is when you put a new row in. Update is when you change something, like change somebody's GPA from 3.0 to 3.2. Is it possible to take some other row? Yeah. Well, it depends on what the type is. Okay, suppose there are booleans, then there's no point in taking the sum of booleans, right? So it depends on what the column type is. Mostly applied for numbers. Like sum is really only applied for numbers. Because you cannot sum any other data type. You can sum complex numbers, but that's weird. Okay, sum reals and imaginary separately. Or you can sum vectors, right? It's also pretty cool. You can sum the components. All right, so insert, I'll get to select. And then update is when you're just changing something, okay? You're just modifying something. Delete is when you can actually delete data. Commit and rollback are like GitHub. When you do almost any of these operations, you're actually operating on a copy of the real table. The real table is stored somewhere else. You're operating on a copy. Locally, the registrar modifies, your enrollment, GPA, all that. But then when they want to commit, then all those changes that you made locally are permanently saved. That's a commit operation. And if you didn't commit, then locally you can roll back and then just make all the changes you locally made and throw it away. Then you can start over locally, and then the main database is not damaged, okay? That's all rollback means. So those are pretty simple. So commit permanently commits and rollback locally rolls back. Meaning when it's safe to commit, then commit. Then if your machine crashes, you didn't lose anything. Conversely, if you screw up, then be thankful that you didn't commit. You can just roll back. Then nobody knows that you screwed up. So you can test lots of SQL, and if things don't work well, then you can roll back. Okay. So those are like classic, repository kind of operations. So overall, almost everything that I told you. Order by, it's just visually grouping something. So if I look for, I'll come back to that. Well, because, it is manipulation. Well, manipulation in the sense, any operation that you do on data should be called data operation language, okay? Maybe not manipulation. Yes. So what you're saying is select is read only. You're not modifying the data. You call it manipulation. Well, you have to call it something. It's not definition, right? So manipulation is a better word. That's all. Okay. So ordering is visual ordering. Say I want to order a bunch of students, their names. It's nice if it's alphabetical. Or I'm ordering a bunch of people's salaries. Like how much money do all the engineers, different type of engineers make? And find all their salaries. But I'd like to know from small to large. That is all order by means, okay? So I purposely explained everything verbally except the top 4 right here. Select, where, group by, having. So in a way, almost all of SQL is all about that, okay, like right there. Even group by and having, they're called like subtotals, right? So you don't need to do this that many times. So in a way, it actually is all about select and where. Very cool, right? Okay, so select, where, group by, having, those are the things you have to really understand along with the exists. And then you're all set. So it's not hard at all. Let's do it, okay? All right. We'll keep using this very simple Amazon-like model over and over so you can picture it in your head. So see you're an Amazon customer. You have your Prime ID right there, and then you have all this other information. They store 100 different things about you. They even probably know your race, okay? And then they can guess your education level. They can know how much money you make, if you're married. They know so many things, but they're all columns. Okay, but the customer code is the main primary key. A customer orders many times. During COVID-19, we order many times a week. Each time you order a bunch of things, that is called invoice. That is what they give you a tracking number for, then all the boxes. So the individual boxes in the invoice, they can all come together, they can come separately, but it's considered one order, okay? So each order is called invoice, and each invoice has a number, and in the number, obviously, it says, what customer ordered it, and then when the order was placed. So that makes a lot of sense. A customer can generate multiple invoices, or somebody not spending any money. What is in an invoice? Individual items. Those are called line items, literally line by line by line. They're called line items because each line can be served by like a different uh, employee. So employees who work in all these massive Amazon warehouses, their job is to satisfy these line items all day long. Everybody has a small monitor, right? A line pops up in front of them, like a small mouse through a maze, like a rat through a maze. They would run and find out where their object was and run right back and pop it in a box. They are timed, by the way. It's crazy, okay? When Amazon first started, they sold books. So they had warehouses, some books. But the warehouse books were not organized like a library. In a library, it's pretty interesting. It's about randomization. In a library, books are organized by, math, philosophy, the Dewey Decimal System, right? So some books might be pretty far away because of the organization. So Amazon purposely threw all the books with each other, made a pile, and made the employees memorize what is where. And they learned that on the average, it is faster to retrieve that than to actually sort it, okay? It's weird stuff. And if you're not very fast, they're happy to fire you and get somebody else, okay? So humans are like robots until the actual robots can take over humans. There's some automation already, in terms of like packaging and so on, but slowly they'll get rid of all humans. So this warehouse look massive, okay? You go into Costco and you go, oh my God, what the heck? So this is like 10 times Costco. And those are the poor employees that I'm talking about, okay? So they're all timed, okay? Every single one of them is a little line item. They can run and get it as soon as possible. Flash drive over there. Shampoo bottle over here. Paper towels over here. They just know, okay? I mean, look at this. It's just insane. All right, so this is what happens to all the line numbers. And then they have automation. They have like all kinds of things that deliver stuff to them. Weird. Work hard, have fun. Those two things don't go together. Jeff Bezos couldn't care less about have fun part. He just tells you that because it's a cool thing to say. Work harder. Okay, so line items, right? What is in a line item? The invoice number should know where the line item came from, like, whom to send it to, and then line number, that's like a primary key, the combination primary key. And then product code. So the main thing is, what did they order? Products have product code, like right there. And then how many items did they order? 10 boxes of cookies. And then what is the price for each? So these all make sense. Then you can charge them that amount. This way, do the product vendor. So that single number can tell you all about the product. Sony laptop, there's a number for it. Sony laptop. So laptop, and when did they order? Quantity on hand. So this is the product catalog, by the way. It doesn't matter who ordered it. Every single product Amazon sells, all the millions of products is here. So for every product, they'll know when they last bought the product from the vendor, from Sony in this case. How much they have left. This is why it tells you 8 left, more coming soon. Order soon. So that's coming from quantity on hand. P min means how low should the inventory get before you reorder. So maybe you have quantity on hand is 8. This might say 5. So if somebody buys 3 more laptops, automatically it'll be reordered and this date would be updated. So that is how much least you can afford to have before you run out. It's not 0. And what is the price for each, and what discount can you give to the customer, and then who made it? Sony made it, right? So Sony is over here. Every vendor is just a number, and you can find out everything else about the number from the number. Very easy, right? Just a small little ordering thing that makes Jeff several tens of millions every day. The guy gets richer and richer. SQL data types, they're pretty simple. They're like JavaScript or something. So it comes with the least possible data types. You have to have numbers, okay? So, I won't spend almost any time actually telling you like what these are, so please Google it, okay? They're just different like number specifications, that's all. Likewise, char, varchar, I'll just tell you one difference between them. This tells you like how many characters fixed size to allocate. Like a name can be 20 characters or less. Varchar is variable. It can be anything up to that, okay? So it's like, a little bit more efficient, but more processing. But you can find out the difference. So number type, string type, date type. There's also a Boolean type somewhere, yes or no? So least possible data types. Then if you wonder, I want to make a geospatial coordinate system. I want to store like people's locations. You can make your own class definition, okay? Yes, class definition. Just like in C++, you can write your own class definition. You can write your own class definition for SQL. Then you can put in new data types, like new members. For example, geographical coordinate would have an X and a Y, longitude, comma latitude. Or you can make a vector for your missile or your quadcopter to point to a certain orientation. And I can have the vector have 3 components, X and Y and Z. I can make a color class and have RGB components. So we're not limited to this at all. You can make your own type. but this is what comes with it. By the way, varchar2 is the variable character, not varchar. Varchar is currently actually undefined, which is a little weird. You would think that 2 is undefined, but 2 is actually there. And then 1 is the one that is not defined. Orafact is an amazing site that can tell you much more about SQL. So please start looking at Orafact, okay? You can answer a lot more questions for you like this, yeah? And to give you examples. All of these you can actually paste in interfaces. I'm going to show you pretty soon. Because Oracle set the standard for SQL, so other vendors pretty much follow that same standard. Even though it's called Orafact, it's basically portable SQL. I can copy and paste this into any SQL implementation. It'll work. Is homework 2 in SQL? Yes, it is. And also, homework 2 most likely will tie back to homework 1, which means you have to take your table design. Yeah, right, exactly. So we use varchar 2, right? You can tell. If you guys have actual practical real world information, please feel free to share there. But I haven't shown you real examples, which I want to do now. I'm itching to show you examples. Okay, so dates, just date. Creating table. By the way, date also depends on locale. It means depending on whether you're in Europe or India or the US, they might store dates differently. And the system just knows what to do. Like, month first, day first, year first, whatever format you want. Those are just simply views, It's not the actual model. There's only one date, type of date. So table structures, now I start to show you actual definitions. So how do you create a table, right? They're like a function call, but the function parameters, I can have all the parameters next to each other, but here we just put them one below each other. Just look nice. Yeah, MySQL, okay. Yeah, I like this. Keep going. Use spaces to line up, table names are capitalized and not null unique, create table. Okay, so in the end, create table is this command. Create table, what table name you want, parentheses, and inside all of the column names, what should be primary key, what should be foreign key, check, constraint, unique, no, all of that here. So time for an example. Primary key is also specified right within the parentheses. Then it's a command, so you'll actually have a semicolon, like good old C++. And then we can do the whole cascade, okay? So cascade means when you create these tables, you can set it up so that some primary key that is dependent on this, some foreign key rather, that is dependent on this primary key. What can happen is when the primary key is gone, the foreign key row can also automatically be gone. This came up in previous lectures, right? When I talked about employees and dependents. So if you don't want dangling null pointers, set up cascade delete. So when the primary key row is gone, all the foreign key rows in many tables will also automatically be gone. Or when you update something in the primary key, you can pass the updates to other places. Those are called cascades, okay? So cascade delete, cascade update. Okay, so examples. The product table that we saw can actually be created with this example. Create table, product table name, parentheses, parentheses, semicolon. Everything else inside is all about columns, attributes. Product code, what type, string type, this is primary key, not null unique. Product description should also not be null, because in Amazon you try to search for laptops, right? And half of them they're not called anything. Like, well, what the hell is this called? So we should not leave that null. So even though it is not a primary key, still make it not null. And then invoice date, we should know when we last ordered, right? It should not be null. Quantity on hand, again, you want to have millions, so make it a small integer. These are all like differences between, data types, okay? Like in C++, you have byte, short, long, double, long. So stuff like that. Small int, not null. Pmin, price is a decimal point because of dollars and cents, 2 decimal values. Discount, again, how much percent or how much money, in this case, real dollars to subtract. Vendor code. And then this is repeating information. We probably didn't need to say this here at all, because you can just say primary key parentheses P code. So you're just saying there's not null unique and primary key. You're saying it twice. What do you think? But 2 is a giveaway. Anybody? So what does 8 mean? What is 5, 2? Keep guessing. Foreign key is, so this is a product, right? In the product table, what is the key that is going to refer to somewhere else? It's the vendor code, right? So you're saying vendor code in this table is a foreign key. It references a different table called vendor on update. So if you update the vendor, then that means automatically this table will then get the updates as well. Exactly. So max 5, because it can be up to 5, because not everything that Amazon sells would be like 5-digit dollars, right? 2 is 2 decimals. Okay. So 5 digits dot 2 digits maximum. How do you do composite keys in SQL? You can actually have commas. You can say primary key, P code, comma, something else. First name, comma, last name. So what is so cool is you can literally go here, right? You can ask me, I'll tell you, but you can also do this as self-service, like right there. and start giving examples. And then you can copy and paste all these examples into real things, okay? Into real SQL implementations. So like that, just do a comma. So you can do a comma for as many as you want. So that's what you're asking. All right. And then you can copy and paste these real examples, okay? Okay. Many ways to learn SQL. Okay, I want to tell you more though. All right, so this seems like very straightforward in a way. Ultimately, this just says that's how you create a brand new table. It means I have all the columns but 0 rows. And then this just tells you what all those things mean. So not null means you cannot leave the column blank. Unique means each should all have separate values. And default is when you don't specify, they fill in the blanks for you. And check means it performs some kind of a a sanity check, a validation check. Like, salary cannot be negative, date of birth, cannot be like more than like 1985, stuff like that. Okay, so again, on update cascade, on delete cascade. So an update cascade means when one column is updated, that update would be reflected in all the other places that want it. Delete cascade, if I delete one row, all the other rows that are pointing to it will also be deleted. Okay, so then you can read this. Cool. Data manipulation. So this is again insert. So how do you, now I have an empty table. How do I put one row of data into my table? Just say insert. Insert into the table name. It's almost like an object because a row of data is like an object. Okay, so you're saying create a new object, instantiate a new object, and here's the constructor, and here's the values for all the the members of your class. That's ultimately what it looks like. So I'm going to show you insert into product, and then you say the word values, and within parentheses 1 row's worth of actual product code, actual product description, actual price, actual what, and then that single row would actually go in your table. That's pretty cool, right? So simple. And there's all kinds of shortcuts for this. Used to add table rows with not null attributes. And then commit. So commit is again when you are locally doing work, and then just say the word commit, and then all your changes that you made, will just be then sent to the actual real database, so to speak. Because you are not operating on the real database, for good reasons. If you screw it up, then it's basically gone. Restoring takes like so much time and energy. And so you don't want to just constantly restore things because somebody screwed something up. It's the same reason why you go to GitHub and you pull down a repository and you locally make all your bug fixes, make all your changes, screw up. Only when you say that you're better than like what you started with, then you can actually just do a push. Same reason. So you work locally and then you commit. Every time queries run, by the way. So if you have a query means, by the way, not just questioning. Query also means updating data. When the query successfully finishes, in many implementations, automatically there will be a commit that is added. In other words, if the registrar locally changes your GPA, then it'll actually get written to the real table somewhere else. Cool. Okay, so insert examples, okay? So you have to read it like this. Insert into vendors space values. It's not insert into values. Insert into vendors space values. This is exactly the data for one row. This is a vendor, right? Vendor ID, hopefully the ID is unique. Vendor ID, vendor's name, vendor's area code, phone number, state. Yes. Are we still current with the vendor? This is also old, right? There should be like, all kinds of like Twitter handles and, WhatsApp phone number, like all kinds, email at least. Okay, so this is like old stuff. Insert second example. Just see if you really do this, after having done this, you will get 2 rows of data. So you made 2 vendors from scratch. If a new vendor wants to do business with you, like Amazon, right? Anybody can sell through Amazon. So they're constantly adding probably several hundred of these, per day. So you have to submit your information in a form somewhere. Then they grab the form data and they do this. Then you become like an Amazon, like a reseller. All right, I guess they become your reseller. And then insert into product value. So now go in the product table and do the exact same thing. These are the things I want to sell in my hardware store. Every single product. This is a unique primary key for the product. Product's verbal name, and then all the other information, right? When do we order the product? And then, what is the quantity and how much does it cost? What is the discount? No discount. And then some other number. Oh, the vendor who made it. Okay, the last thing is just the vendor. So simply add row after row after row. Again, Amazon has like millions of these. And then this one more example. If you have no information for a vendor, you don't know who made that, right? You can say null, and then null will literally leave that cell blank. Okay, you can say null. But if you do this, what if you only know the product code and the product description? All the others you either don't know or you don't care. If you do it this way, you're forced to say the word null, null, null many times, right? Because it's like a parameter, it's an argument list. You cannot leave things out because then it'll tell you that information is missing. So if you don't know this, then you're supposed to, say null, null, null many times, and that seems wasteful. So then there's an alternate way to only specify the information that you want. It's key value pairs, okay? So you say insert into product, key values, value. It means I'm only going to supply P code and P description. Please leave everybody else null. This is a more efficient way of saying this rather than saying null. It's much simpler. Literally, what member name, what member value. It's like programming, okay? You can do this in many programming languages, like in JavaScript, you can do it, Python, right? Just simply variable equal to value. Then only that variable you're passing, and everybody else, hopefully, there's a default or null or something. All right, so that's an efficient way to only specify part of the information. Again, like I said, it's like parameter passing, and then the compiler does matching. That is why you cannot leave it out. You must say no. If you leave it out, they'll think that you forgot. So you must at least say no. It must match in position, type, and count. Again, like programming, if you do it like this. You cannot have the primary key right at the end. It's weird. It'll tell you, well, that's not a string. I was expecting an integer. So it must be in the same order that you specified in your table. So when you create the table, your data should also be specified exactly in the same order, unless you do key value pair. If I do key value pair, I can say for some product that I'm not going to give you information yet, the price is $10. The description is it's a hammer, and then product code is 1, 2, 3. That you're allowed to do. Otherwise, if you do the standard parentheses, like the first few examples, you must supply all the values or you must supply null. All of what I've said so far make some just common sense, okay? Like, why did I have it this way? Well, because, any other way is ambiguous. Like, it doesn't know what you're trying to do. So just make sure that you do it the right way. Okay, so far so good. Select, the biggie. This is the real reason to learn SQL. Because select is what goes in every single query in the world. And query is really data mining, okay? Query is data science. Big data, query. It's all about querying. It doesn't matter whether you have 100 billion rows or 10 rows in your data. It doesn't matter whether you call it NoSQL or SQL. Nothing matters. You're ultimately selecting, okay? Select. It's all about select. Okay, so select is very simple, the syntax. You just simply say select a bunch of columns. So give me a bunch of, first of all, give me rows really. But for the rows, the question is what columns do you want? Do you want all the columns, just some columns? So just some columns. Like tell me just a student's first name and last name is enough. From the student table. It's very interesting that syntactically speaking, just grammatically speaking, this is all you have to do for the select command. But this is the world's worst select command because you're not really selecting everything. You're not selecting anything. You're selecting the whole table. Suppose I say select first name, last name from USC students. I'll get every single USC student, first name, last name. If I want to see it, that's cool. But in a way, that's not very useful. It is more like just visually make sure that all my data are there, okay? In other words, what is missing in a big way is over here called where. That's like an if statement. So select first name, last name from USC students. Where? Something. The student plays, 3 kinds of sports. So the where is really all the filtering. That's where the filtering happens. But the filtering is not part of the SQL syntax. SQL syntax should be as simple as a bunch of columns and some table. Wow. Actually, you can have more than one table. Then all the columns from all the tables would be returned. But the magic is the where command, okay? The where subcommand. Okay, we don't have that yet. Update is all just simply modifying data. So what if you update the student table for some student? This is where the first student comes in. Set GPA equal to 3.9. All of a sudden you want GPA to be 3.9, but not for everybody. If I say update USC students, set GPA equal to 3.9, every student will get 3.9. But now you say where student ID equal to your ID. I just put in your ID, then only you will get 3.9. So where is what is restricting? Where is like an if statement. Select is like a for loop. Okay, the word select means do this for all the rows. Where means if. So you have a loop at the end and then an if statement inside. That's ultimately what is happening. Like here. I'm going to be bold and do this again, okay? Yeah, select accepting the no. See, don't get this mixed up, okay, please. Yeah, it is in a way, I'm not saying that's the wrong answer, but they're two different ideas, but it acts in the sense that you are trying to name just a subset of columns, okay? So I'm not dismissing Asia because there's a separate project command. In the separate project command, it won't filter anything. It'll give you just only the columns that you want. But yes, when you say select a bunch of column names, then it is like project, okay? Sorry, Asia. You are right. It's not like I meant to say no. But they're two different things. All right. So when you have a table of data, ultimately select and where. This is what happens. Just select and where. I got all this information. Then here's the GPA column that we all look at for so many reasons. So 3.9, 2.7, 4.0, 3.86. 40,000 of you, and all your student IDs are here. So any select operation, by definition, would go through like all the columns, all the rows rather. Select means for every row, select. But when you say select where means if statement. So that's usually why we say select first name, comma last name, because hopefully there's a first name and a last name column. I don't want all the columns. I don't even want the GPA because I'm going to specify it. So select first name, last name from students. So this whole table happens to be called students. This whole table is called students. Students like that. If you just do this, if you simply run this, I'll get every student's first name and last name, all of you. But I want to know only people that are more than 3.5. That is where the if statement comes in. So if, would you stay where? GPA equal to 3.5. That's it. So this acts as a filter. So this says for each row, if that column is true for that row, then output the first name and last name. So it's ultimately looping with a little branch inside. Okay, this. So loop everything, and only if a condition is satisfied, then spit something out. Otherwise, just keep looping. Just keep on looping, and then for all the things that match, filter it out. So the result is a select. Select means a restriction of the row. So in this case, only these students, these three we're going to get. The student we're not going to get. And also another restriction, like Isha was mentioning, in terms of the columns, you don't want all the columns. You only want a 2-column table. So cool, right? So this is really the magic, okay? But I'm going to tell you something. Okay, so these conditions can be more complex. This is actually pretty easy. You can say, GPA and then you can say major equal to CS, like all that, okay? This is a major column. But what can actually happen is you can have another whole select command. You can have select something from something where something. So then that select would run and then feed values for this one. And then this select will run. So this is where the complexity comes in. As a matter of fact, even here, I can have a select something from something where something. Wow. I can even basically make a brand new table and then from the table do another select operation. Wow, right? I can even make this into select something from something where something. So you can even make brand new columns from existing tables and then select something out of those columns from these tables. So it's pretty much like, cascade, 3 raised to n kind of a deal, where initially I only have like, 3 select from, where. But then each of those results can have select from where. And each of those can have select from where. So you can have a cascade of queries, and that is where the complexity comes in, like, wow, what does this whole thing do? So if you see a very complicated query, these are called subqueries, then you do the usual thing you do in programming. Run only that little piece separately. Just run only that, forget all of this, and see what it does. And that way you can understand what the main query does. So a very complex multi-page SQL query is not hard, to understand. You do it in pieces, just like in programming. Just run one little part, isolate it, and then you can understand. So in the end, I'm not going to say, it is a very hard language. It can be complex. The queries can be quite complex, no doubt at all. But, after a while, you actually become an expert in looking at a query, and you instantly know what it does. That takes practice. You've seen it so many times. All right, so that is what select is. Okay, I cannot tell you enough about select. There's a lot of select. Okay, first things first. This is very simple. Star means all the columns. So why even bother naming columns? Just say star. When you say select star from something, it'll print you the entire table, all the rows, all the columns, like a visual check just to see that your table looks good. In reality, you would never do this. If Amazon does this, okay, for the customers, they would see 100 million customers, okay? If they scroll it on the screen, scroll for hours, really. And it's useless. You cannot learn anything from it. So you do this just for fun once in a while on small tables. But this is more commonly done. Select only those columns, but for every row, no filtering of rows. I want to know every single product that I have in my store, but I only want to know this information, not any extra information you might have, like product rating or something, safety rating. Update is when you literally modify data. Update that table, literally set that column equal to that value. So the one cell will change, okay? So just one cell data will just change that as update. So I have like all this data, again, for this one product is going here. That's the price column. Just change the product's price from $2 to $2.20. Just increase the price by 10. And there's automated ways to do this, by the way. You can run other queries that can actually go and do this, but you can manually just set, if you know the product ID for that product. In other words, set that price column to be equal to, $2.20, where product ID equal to the product ID they want. You can even set more than one. They'll all change no matter what they were. They'll all be that. Okay, so you will learn lots of things. Likewise, rather than set something, you can multiply. You can say the new price equal to old price times 1.1 for certain products. They'll all then become 10% more expensive. Or conversely, you can put things on sale. You can say for certain products, make the price be like times 0.99, then it'll be like 1% off, and so on. Just numbers. But here we specifically only set that invoice date. Say you reorder this product, you just ordered this on this date. You have to reset the invoice date. That's what's happening. Then you will know there's some more recent invoice date. Doesn't matter what the previous date was. One more update example. You can update multiple things, okay? So then for the product code, you reorder it. You also change the price. Maybe a version 2 came out, the price went up. So those are real world examples. And then p min equal to 10 means when it goes below 10, then reorder and then set the new date. Okay, so this all makes sense. So select operates on one or more columns, 0 or more rows. If your select condition is extreme, okay, then you don't have to get any result at all. Suppose in this hardware store, you say select, product description, where price equal to $1 million. There's no product in your store that costs $1 million. Then you'll get empty result. So on the one hand, select will return you an empty table with 0 rows, 0 columns, but still mathematically a table. On the other hand, select will return 100% of all rows and all columns. Those are two extremes. In the real world, it's always in between those two extremes. Cool. And then select, like I said, is called a set-oriented operation because you never say for all rows or anything, right? Just simply just name what you want to do. It does it for you. So it's called set-oriented programming language. Sometimes it is called a non-procedural programming language. In a procedural programming language, you would have row IDs. So you would say for row is equal to 0 through, like count rows or something. And then you would literally do the looping and branching yourself, which is fine, like a programmer. But here you don't have to be a programmer. Just express what you want and it finds a way to do it. So update modifies one or more columns on all the rows if you want. Like I said, you can just say, update student table, set GPA equal to 4, all students, wow, perfect. The whole school graduates with 4.0. But normally you don't do that. Normally you say where. So where is where the restriction comes in. Where is the if statement? Okay, so you can read more about like all these things. This one, modifying rows with update. Like update set column equal to from where condition. So once again, just try and like do all of this. Say you're a library, book or bookstore, then you would do all of this. ISBN means a specific book's primary ID. Every book has an ID like this in the US, ISBN. There's something called ISBN 13 with even more digits on it. Okay, so then you can update whole columns for all the rows. It doesn't matter, like all that, okay. Okay, so we'll do things like limit all that pretty soon. All right, so if you want to read more, just give you some extra links there. Okay, so data manipulation, this again, the where condition. So where is what tells you, what restriction, what filtering I want. That's what makes it all useful. Otherwise, what is the point of saying, the same thing for everybody? Okay, so rollback is the opposite of commit in the sense that rollback is local. If you are working and then you commit and then afterwards you worked again, then you can roll back. So it's like this. Suppose time went like this. And then your real database is over here. Your local database copies, over here. So you're working, and then you've done some operations, and you've done some operation. At this point, if you say commit, then all these changes that you made to over here would get copied to over here. So now a permanent change has been made. Like a checkpoint. Then you can start doing more operations. Suppose you commit over here, then those changes you made, those extra incremental changes, would get written out to like over here. Then you make more operations, more. And here you screw up and you delete like half the table by accident. You go, oh my God, what did I do? So then you can do a rollback, and then the local changes that are kept would then restore your local table to where this was. So from here, all these changes would get thrown away locally. So you'll get your table back the way it was when you did the commit. So this is all forgotten. Then you can do it right again, and then you can commit. So rollback is local, okay? It means only this is affected, this is not touched, because it's hard to roll back here. To roll back from here, you need what is called system logs, where there are text files that are written, that every time you make a cell change, it'll tell you what table, what row, what the old value was, what the new value was, what the timestamp was. And you have to go in the log file, then here's the new value, here was the old value. So then you have to look up the old value, update the new value by it. So literally like roll it back using a log. It's more formal, more difficult. It means during that time, other people cannot use the database. All right, so, for all those reasons, definitely you do rollbacks locally. So commit can be made when you're sure that there's no need for rollback. You would do commit in case you lose data, when the power goes out locally. Suppose you didn't commit at all day long, you've been doing local operations. Your table looks amazing, okay? And at this point, the whole power just goes out. You'd lose all the data, because it's in your RAM, right? Nothing was even saved. It's like saving your Word document. It's all the same thing ultimately. So whenever you're sure of committing, you should actually commit. Like Dropbox even does it automatically, right? So in Dropbox, previously before Dropbox, we had to sync things manually. But Dropbox basically says, forget this, we'll do it for you. Every time I make a change, that'll automatically update right there. It's magical. It's a good thing. It's too many commits, but we don't mind. All right, so rollback, delete. So delete is just delete the table, delete columns. You can even delete certain rows. Like say a student leaves USC, you can just say delete from student table, where student ID equal to, then the student would be gone. Or the product you're not selling anymore, delete that. So say the manufacturer recalls this product and says nobody should be using this, hurts people. Then you want to delete that from your catalog so nobody can order it. All right. So you can do any kind of deletion. You can even do this. You can say delete from products where the product minimum equal to 5. So anything that has, a PMIN of 5, for some reason I don't want to sell that. It's like a weird example, but you can do it. What about this? So what if you say, delete from product and there's no where condition? What happens? Oh, stack trace is created. Yeah, there's some kind of a stack trace that is created that is correct. And then any advantage of not using on update cascade? Only historical reason. Because if you don't use the cascading, then you're going to get basically, inconsistent data somewhere. So unless you have a strong reason for wanting that, delete the cascade is the norm, just so you won't get like bad tables. Rollback goes to version 1. Can you set a different version? Yeah. That is system dependent, by the way. That's a very good example. You can actually roll back to even like earlier versions, okay? It's just like a config somewhere. Yeah, exactly. If you just delete from product and there's no where condition, your whole product database would be gone. Yeah, so you must have a condition, right? Again, it's practical. You can try all this, by the way. You can make a small table with 5 rows and just say delete, so what happens? It'll all go away. Inserting. Inserting is also easy. Just say insert into table name and then select some columns and just insert what you want. This is a lot like creating the rows in the first place, okay? But now you're doing it to an existing table. That's the difference. Add multiple rows to another table as a source. So this table already exists. Now you're adding more rows. Say you already have a car dealership. You bought another car dealership. You want to take all the new employees and add it to your existing employees. And that is insert into. So do you, yeah, right, exactly. That is exactly what cascade is, Molly asked. So when you set a cascade delete, when you delete the primary key row, then it'll delete all the foreign key rows so that the foreign keys will not point to null pointers, okay? That's exactly it, good. It's all about not pointing to nulls. So what Molly was asking was pretty much, that say you have a primary key here. This is a primary key, 4. So now there are so many other tables where the same column is a foreign key. Say the column is called A, okay? So there's A here. And some other table also has the same A, but it's also a foreign key. And then there's some row that has got 4. So that 4 is being used to get all this information. And then in this table, there's also a 4. And this 4 is used to, again, look up that information. See, if this person is gone, right? And those other tables don't know about it. Say you're trying to bill, the patient like for the procedure that they had. They try to find who the employee was so they can take it from the salary. The employee is gone. Wow, then the hospital is going to lose money. So to avoid this, when this 4 is deleted, we'll go looking for that column in other tables. And any place that it says 4, then just delete it. That's basically what it is. So that that 4 will not, so that that cell will not point to like a null or non-existent row. I remember, so let's see what people said. Okay. In real life, not tell databases, okay. And then the rollback changes dropped, okay. Yeah. So you're trying to answer like a question or? Yeah, so the rollback is like basically a local rollback. That's really all you need to know. Commit is like, a permanent commit.
Yes, sorry, I just interrupt because I remember that if I'm just saying that about the commit, I don't think every SQL compliant database requires that. Like I remember that MySQL doesn't need it.
Yeah.
But Oracle does. But I have worked with other databases except this too extensively, so I can't comment on others, but there's just examples I can.
Interesting, I like that. Because implicitly, when any query succeeds, there's actually a commit at the end of that query. They automatically insert a commit for you. So that way they might not make it explicit. But if you want to commit even, earlier than that, basically you can have a commit after every single update if you want. On the other hand, if you want all updates to succeed like one long procedure that you wrote, then at the end of that long procedure, you don't have to put a commit manually. because when it's like a function call. When the function call finishes normally, there's no abnormal exit code, then the commit is automatically done for you. So that might be the reason why they don't require it. But that's a good observation, okay? Meaning the programmer always has the option of inserting the word commit anywhere they want. Otherwise, commit is automatic. When something succeeds, that's automatically a commit at the end, because they don't want you to wait for too long and lose data. Okay, cool, very nice. So what CG said is correct. Okay, so moving on. Subqueries. Okay, all of this. Yeah. Therefore, this notion of insert into select, I'm going to show you this, okay? This means I already have one car dealership. Then I'm going to select all the information from a second car dealership and add it to this row by row by row. So that is where the insert select comes in. So you already have one table, and the table already has so many rows. But now I'm going to have this other table and do a select operation and get rows from here and insert that into this table one row at a time. So I can add to an existing table without me manually adding them one after the other. I can get procedurally with the result. Just automatically insert, okay? So that is where the insert and select work together. And that comes as an example here. Insert into table, select column is from some other table name, select table name too. And whatever columns exist here. Suppose this table has more columns. Now we have a chance to delete them. Like this dealership does not store car salespeople's birthdays. This dealership had a birthday column. Don't name the birthday column because that will not translate. So this is your chance to do a project again. Phantom read is a very different operation. Phantom read is a very different idea actually, okay? So this happens when multiple transactions are like reading and writing. So let's completely hold off on that, okay? It's a very cool thing what you're asking. When you're constantly modifying data, so there's a write operation going on. And without locking the table, some other transaction is keeping on grabbing the values. Then you would get things like phantom reads, because every time it reads, you would get a different value. So that's what that is. So it's not connected to like almost anything that I said, but it's a cool idea. So we'll come back to that. That happens when you have multiple transactions. Okay, so selecting rows using conditional restrictions. I mean, this is really the heart of it all. Select something from something, where something. Okay, so it says optional. Very interesting that syntax wise, where is like not needed, but where is really where all the power is. It's funny, it's optional. Okay, so now for the where command examples. And when I show you examples, I might as well talk about those 6 comparison operators: equal to, not equal to, less than, more than, less than or equal to, more than or equal to. And you can do those comparisons on any data type, such as characters you can compare, dates you can compare, numbers you can obviously compare. So any comparison that makes sense in programming, you can just do it. All right, so I have examples for all of those, but we saw this already, okay? There's 6 of them because of equal to being different from equal being different from less than or equal to, greater than is different, greater than or equal to. Classic programming. And syntax you can use like standard C++, or you can use Fortran. It's a pretty old format for not equal to. I think Visual Basic has this as well, not equal to. So equal to, not equal to. Okay, so then comparison operators, computed columns. A computed column is a new column that you can make. For example, in the normalization lecture, we had how much somebody makes per hour, and then how many hours they put in. When you multiply those, then you get the actual amount you charge. That new column did not exist in the table, but then we call it a computed column. Okay, and the computed column can be given a name. You can call it amount to charge, and then that's called a column alias. If columns have no names or the names are too long, like in Python, you can rename a module, math as M or something, right? Likewise, you can have column names. It's called column aliases. These are like convenience things, but this is powerful. You can make new columns, and then you can operate on it. Okay, so alias is the name of a column, computed column. Yes, so I'm going to show all this to you. Okay, so look at this. That's the computed column. Select product description, quantity on hand, product price. These things are in the database already, okay? But look at this formula. Quantity on hand times price. I want to know how much my hardware store is worth completely, how many $1 million, right? So what I have to do is find out all the different things that I sell and how many individual items I have. I have 10 power painter spray cans. I have 32 saw blades, and each saw blade costs $15. So therefore, I have to multiply them to know how much saw blade worth of product I have, and then add all of those together. So when you multiply this, that becomes a new column. So when you run this in a real table, you will actually get this new column. But see, we didn't name the column, so it calls it expression one. That's so interesting, right? Like programming, because that is an expression, just simply a formula. So it calls it expression one. So if your manager looks at that, they might guess what it is, but they might not like, what the hell is that? So you need to rename that, okay? Then it's called alias. You can say QH.price as, and then a column name, and then that'll be replaced. That is what this is, okay? So our next example is that as total value. I guess total value for that product. I would have just called it product value, because total value is actually the sum of all of this, okay? So imagine calling this product value or something, or combined value, something. Okay, then you can say sum parentheses total value and just instantly adds all this up. But our point is we can make brand new columns that didn't exist before by just a formula. Then you can do cool things like, suppose you purchase something someday that is called the invoice date. Like, when did you purchase it? Suppose you want to reorder always 3 months from now, or you actually want to, pay somebody like within that time, whatever the reason to add 90 days, okay? Something called 90-day invoice. You always want to add 90 to an existing date. So this plus 90 is very clever. It can take, into account some months of 31 days, some of 30 days. February oscillates between 28 and 29. It knows all of that. So the plus 90 will magically put in the correct date, okay? So these are conveniences, because otherwise the programmer, the user has to sit there and manually look up a calendar. But the plus 90 always knows, what plus 90 is, and make a new date for it and call it the expiration date. So here we're using plus 90 for expiring. So say this is food. Say this is bread, okay? So every time you purchase bread, you cannot sell it for more than 3 months. It has to go on sale or be thrown away. So that is why you add the plus 90. Okay, cool. So these are all really useful things. And then this is classic programming when I have, multiplications, additions all like thrown together. And it's going to do classic operator precedence unless you use parentheses to disambiguate. For example, if I do 8, so let's actually confuse people like this. If you do this, then it's definitely not 13 times 2, right? You would know that. It's going to be, 10 plus 8 is 18, because multiplication goes first. But if you want to be sure, you can always do this. Or if you want to be sure of the other thing that you wanted earlier, then you can do that and not do this. So just disambiguate. Things like exponentiation, multiplication, division, they have much higher precedence than addition and subtraction. That's all there is. And you know this from other languages already. So like that, okay? So if you have parentheses, that overrides anything else. Otherwise, normally, exponentiation, multiplication, and division, they're equal, because, it doesn't matter what order you do them in. And then addition and subtraction. Again, it doesn't matter what you do before what, when you have them in one expression. Cool. So then these are the simple mathematical operators. There's no modulus operation like Python or something, right? Okay, so addition, subtraction, multiply, divide, exponent. This again, old-fashioned languages. Exponent. Hat. What is the hat symbol called? It's not called hat. In programming, we call it. Yeah, exactly. Caret. Very nice. It's a caret symbol. Not carrot, the kind of carrot that you eat. Carrot. Very good. Like diamond carrots. All right, so far, SQL has been very easy and fun, right? It'll continue being that way, I promise you. Now we can start doing like more, lengthier calculations. Okay, so select a product table, logical OR. How do you do an OR operation? So how can you say, give me all the products made by this vendor or that vendor? Then you will only get a subset, right? Literally, right? Like an OR operation. So tell me the product's description and when we ordered from them, the price of it, and then the vendor code for either this vendor or that vendor. So again, go in this and search. Anytime any row says 21344 or 24288, but not something else. In fact, this is the result, okay? Say our table had many more vendor codes. Then the result of running this operation would be that, because you can actually see as a visual check that it's only this or this. In the real world, suppose you give it to somebody, you would put that in to make sure that your query is doing the right thing. And afterwards, you would delete this column, just take it out, because it's obvious what you're going to get, because you specified that in the first place, right? So no need for that. Okay? So in production, you wouldn't ship this, just comment it out. All right, so OR was like super simple. They're all simple. And is also super simple. So what if I say this and this, okay? So this and what? So then how do you do that? You cannot obviously say this vendor and that vendor, that's not logical, but so you'll use a different example. Again, this is the result. Give me the product description, invoice date, price, vendor code from product, where price is less than 50 and invoice date more than. So tell me all the products that are cheap and also that we ordered after that date. So you can check, okay? It'll be only the date or after, Likewise, it'll be only 50 or less from the millions of products that we used to have. So then that's all it is. Cool. And then you also want to know the vendor code. This use your chance to say, wow, we don't even know who makes that. Okay, so that's the AND condition right there. And so there's no end to how many ANDs and ORs you can do, okay? So you can have many ANDs, ORs, NOTs. It's basically programming. It gets very powerful. So to that point, you can combine ANDs and ORs. Now, how would you do that? Like this. So again, select product description, invoice date, price, vendor code from product table, so far so good, where this more complex thing that says what we saw before in the previous slide, or this entirely different condition altogether. So tell me all of these, and also this. Therefore, you might see a 2488 for which that condition is not true, right? It's not more than 2014, but that's okay because this condition was satisfied. So anything where this condition is satisfied or the condition is satisfied. So union, okay? So all of this is true and also all of that is true. Okay, you say or obviously, you're gonna get that. Easy, right? It's a classic or. Set union, a set of all the rows that satisfy this, and also the set of all the rows, union set of all the rows. Obviously, something could satisfy both of them. Like that vendor could make a thing with price like $20, and then we ordered from them, like last year, and that's still okay. Again, it's classic or, so A or B can be in the middle as well. In other words, the intersection can also be part of the or. Easy. So these are just mostly conveniences except for the word exists, okay? So between is just a lazy way to say like two different, like less than, and also greater than, say between. You can check if date is between a certain range. Like give me all the people born between 1970 and 1980. You want baby boomers, everybody between like, I don't know, 1960 and 70 or something. Likewise, you can also do a between for GPA. So give me all the students between 2 and 2.5 or between 3.9 and 4. Any range, okay, just for a simple little single range, meaning A comma B is between. Okay, again, some examples. And then this is quite useful, okay? So if for any reason there are literally null cells are empty, then this will give you all the empty cells. Say you want to go and fill with data afterwards. Then you can find out who the null vendors are. Like what products do I have in my store? That if the product broke or the customer complained, I have no way to send it back because we don't even know who we ordered the product from. Then you have to look for the null and as quickly as possible identify what the vendor was so you don't lose money. Like is literally just a string match. This one you can say, give me all the people that start with the letter S. Give me all the, I don't know, customer names and product names, anything at all, okay? Like it's just a regular expression. It's pretty simple, regular expression. And in is like a, or like I can give you a whole list, this list checking, like a Python or JavaScript for loop for something in something. So I can give you a list of a whole bunch of vendors, and as long as my cell has a value that is in this list, it matches this or this or this or this or this or this. Rather than write 20 ors, I would just say in and just do a comma separated list. It's much simpler to write. This really just or. Exists is the more complex one, but it's not hard either. When you say exist, there's a select something from something where. Afterwards, you say where exists or where not exists. And after exists, it's a whole select from where. And you can keep going. So when this happens, I'll just tell you, then show you the example, is that subquery after the word exists will run first. And then afterwards, the main query is going to run whether or depending on whether the subquery succeeded or not. So I can have a main query, select something from something, where something, but now it has the word exists. Then I have another query right here. This query, entirely separate from this query, except some columns here are also common with some columns here. That is the connection between them, okay? Otherwise, they're completely separate. Okay, so this query is run first, like a function call, and that goes in all these tables and get all kinds of information, what, right? But then if this comes back with any result at all, even one row is enough, that row will have that column. That row is going to have that column. And so then that column value is going to be used to match. In other words, this query is going to run based on the results based on those column values. On the other hand, suppose this starts running and it came back with nothing at all, 0 rows were returned, then this main query would silently fail. So exists is very interesting. You can also do not exists, okay? So not exists would do the opposite of what I said. Supposing again you do all of this and you come back with exactly 3 rows, then what will be returned back is not those 3 rows, it's everybody else other than the 3 rows. And so then based on all those values, the main query is going to run. So exists is a very interesting, link in SQL. Okay, that's what I'm going to tell you. So I'll show you some examples. I'll show you one or two and you can figure out the rest, okay? Like an exercise. And then we can discuss on Piazza. Hey, speaking of Piazza, I still don't think that the entire 100% of the class is on Piazza. And if I were you, I would be on it right away. You know, we come up with so many things. We bring up so many things. You're losing out. So please be on Piazza. How do you be on Piazza? Go and just register like right there. If you have any problems registering, right, just send mail to any of us, all of us. Yeah. So we'll add you instantly. All right. So like this, okay. First of all, some between examples. This is very simple. So tell me everything about a product that costs between 50 and 100 bucks. So I can modify this by saying price greater than 100 and price greater than 50 and price less than 100, you know? So rather than have two different expressions, I'm just making one of them, okay? It's pretty simple. So on the one hand, it has to be more than 50. And also it needs to be less than 100. So instead of saying all of this, you can just say between price, you know, and then 100. So it's pretty simple. Just avoid like typing all this. Convenience operator. It's called syntactic sugar. Okay, syntactic sugar. Okay. I'm giving you guys too much sugar. Okay. So then there's that. And then this one is no. Yeah, between is not inclusive. So what do you think? In other words, with the word between, is it less than or equal to, and also greater than or equal to? Or is it strictly less than, strictly greater than? What do you think? It's one or the other. How? Like, what would you like? Suppose there are two numbers here, right? Would you like these numbers to be included or not? I would personally like them to be included, right? Otherwise, it is a pain, you know, to actually put something else so that it's included. Exactly. So inclusive is the answer. So it'll actually include those numbers so that, you know, you don't have any doubt at all about what happened to exactly 50 bucks. Because otherwise, say it is not inclusive. If you want 50 bucks for real, then I would make this 49.99, right? There's no end to that. It's weird. So you want it to be inclusive. Okay. By the way, in configurations, you can actually make it not inclusive. There might be a parameter that you can set so that it drops those values out. Or in the worst case, just go and do it yourself. Just do it yourself. Then you can put in anything you want. You can even have it half, you know, semi-included, right? Okay, so the real symbols give you all the power. And then null is so simple. So tell me all the products where we don't know who's selling it. So then that's literally, you know, is null. Easy. And so then the string matching, there's two kinds of string matching, one for multiple characters, one for exactly one character. So in Unix, again, it'll be star with wildcard for multiple characters. And then the question mark wildcard that matches exactly one character. All right, so that is all it is. So here we'll use percentage instead of star, and then we'll use underscore instead of question mark. Why did they come up with this? I have no idea. They should have, sorry, well, why did they use this? They should have just used the Unix syntax, but they didn't. They picked their own SQL standard, they picked their own. So then it looks like this. Percent means any or all following or preceding, meaning you can have the percent in the beginning or at the end, or even both actually, with some actual characters. Then the match would happen. In this case, the match would happen for any string that starts with the letter J, because the strings are with J. And then it doesn't matter what follows J. Therefore, you know, Johnson, Jones, you know, John, Johnson, Jones, Jerry, and July, all of that matches. On the other hand, when you say Joe percent, then Jernigan would not match because that is JE. So now you have like more condition that you put in. It's pretty, you know, standard and obvious. Okay, this is like a star. It means 0 or more of those matches. So even Joe would match. If somebody's name is Joe, Joe, then that's also going to match that. So 0 or more characters that follow percent. And then this is again preceding, right? So this means ends with an N. So anything that ends with an N. Please try all of these in your own examples, you know, just to understand. But this can be for multiple characters. What if you exactly only want one wildcard? Now, one character wildcard, all the other characters must match. So if I have, for example, A, B, 2, 3, this should not match this. Only 1, 2, 3 or something should match it. So if you want to compare only one character wildcard, make it underscore. And that can be anywhere. So this means it's a pattern where you must have 2, 3 in the location, but this location can be anything. You must have 5, 6, but that can be anything. Okay? And you can combine them. You can have a star and say as long as all this is satisfied, doesn't matter what happens afterwards. You can combine them. Please try, okay? So this is anything that sounds like us, so Jones, Cones, Copes, Toots, Mopes, Zopes, Nopes, all of those. OES. Okay. So then this is how you do it in the real world. Suppose, you know, you forgot the manager's name, you know, the manager name, but I think it's Smith, and it might be Smithson, it might be Smithsonian, I don't know. Then say Smith percent, it'll come up. Jog your memory. Okay, so then customer name like C plus, so now I can start showing you, some of these. So W3 schools, they have an amazing, SQL tutorial. Every keyword that I mentioned is all up here. So we can come back to select all in just a second. Oops, what the hell? Okay, select all. Let's go back here because I want to show you the top, okay? The very top, just start. You can learn like so many things and you can learn SQL. Look at all the things that they put in. Wow, it's a SQL reference. SQL. So this is exactly all of it. So every single keyword that we mentioned, it's all here, okay? So then that is why I was inserted into order by, you can try every one of them. And so they give you an amazing database, okay? That database already has all of these things populated, and you can add one more row, okay? That's really all it is. Okay, so I can tell you about that in a little bit, where I can show you all the different ways in which we can learn SQL. But then for now, just do the select all. So what we had, yeah, select all. And then now we can do a restriction, okay? So first of all, when you say select all from customers, every customer, all the columns. So it's basically all the customers in the little toy table that it comes with. So it has, a bunch of customers, not thousands, but it's a toy database, 91 customers. And then they live all over the world. So you start to see like, where the cities and countries and things, right? That's neat. But now you can say select all of them from, and then you can say, where. So the where condition that I showed you is literally where. So you can, if you want, just you and paste it. So the select star from customers is what we already had. But now we say where customer name. The customer name must obviously be a column that already exists. And you can see it's called customer name. So literally just add the little extra piece that I had, okay? Like that's all we added. Customer name like C star. So only things that begin with C, like for example, like all of these would actually show up. So just run it. Oh, what happened? Let me copy and paste. Okay, so it doesn't like this or? Pretty odd. One more time. Okay. So you see, those are the only people with C star. So suppose you only want like CO, for example, then you can just change it by saying CO star, okay, like this. Just then you only get CO star. By star, I mean percent, you know what I mean? So please try all of these, all right? And so then you can understand. But that's pretty wild, this whole run SQL. This is called live coding, right? You can actually, try it out in the IDE, in the browser. One of the best ways to learn like all of SQL. It's fun, they make it fun. Because you cannot destroy anything. They have the table right there. That's the whole database. That's the whole, database where every single table has all these number of rows. You can even try all these. You can even say, like these are things that people ordered. Suppose you say select star from order details. They actually already have that. Then that's everything, okay? Then you can go into every single product ID and see what it is. Anyway, just play with it. Select star from products. Just do that one last time. You can see what all the things are. Products. The parenthesis is optional. Products. These are all different. It's pretty funny. So suppose you only want the product name, right? Then you would just say select product name. Just go here, select product name. So please try and query this and have all kinds of fun with it, okay? Like find out the total value of, suppose you bought one of each product, then how much would you spend? So this is literally only the product names. Okay. And then you can do product names where, begins with the letter C. Okay, you can have fun with it. Okay, that's pattern matching and, okay, yeah, then the whole or, in like all of that. Okay, so there's a few different ways, right, in which you can specify this or this or this. If you know a range, then you can use between. But this is not a range. Vendor IDs are like random. And so there are two different ways to say, give me all the products that either this vendor sells to us or this vendor sells to us. You can use good old or, there's nothing wrong with it. Or if you know in, make it a list. For only two of them, it doesn't matter which way to it. But when I have 20 of them, I think the list looks much nicer or looks so weird because it takes up so much space because you're repeating this over and over and over again. So you would rather prefer the in statement. And they both are equally efficient, by the way. This actually compiled to that, okay? So in the end, it doesn't matter how you do it. There's a SQL compiler. There's an engine. It's actually very smart. It's an optimizing compiler like a C++ compiler. Even if you do things a little bit incorrectly, it'll actually rearrange your query for you. That's all part of a future lecture called performance tuning. Okay, so during performance tuning, I can give you some examples of how SQL is made to run as best as possible. All right, so in can also be this. So in is going to be a bunch of numbers, right? But the numbers here is statically hardwired. This is like a static query. This is a dynamic query. I don't even know who the vendors are. I'm going to find out from my database today. So therefore, run this first. It's called a subquery. And this will come back with all the V code that it found from the product table. And then select all of that. Then tell me who the names are. That's what this does. If I want to find out the names of everybody that I'm currently doing business with, I have to run this first, obviously, because otherwise there's nothing for this to run right here. So it makes sense logically that this executes first. This is called a subquery. But the difference between this subquery and the exist subquery is this subquery literally comes back with some kind of table, and that table is used in here, okay? In exist, it's more like all the rows are returned, okay? It's like this conceptual difference. Plus, there's a linkage in exist. Like there's some column here that has to actually, also work here. Okay, so my experience is that using SQL for full text, I see. Sure. Yeah, I probably agree with you. You also didn't ask me, what about other regular expressions, So the whole regex, right? This whole world of regex. What if you want to do more complicated regular expressions? You can write your own. So you might do it in some other programming language. The answer, yeah. You probably do it yourself. So the regular expressions, if you didn't know, right? They're amazing. Okay, no, I didn't create patterns. So this one, you can do every possible substitution, like this, right? So it's quite complicated. So of all of those, we just pick the simplest thing, okay? Things like dot, character match. All right, they're called classes, Okay, so people do this all the time. The best language for doing this in the world is Perl, okay? Just for a minute, I can tell you. Perl. The entire language is built around regex, actually. It's weird. Yeah. Why do I tell you all this? Because it's fun. This contest called the Perl obfuscated contest. Obfuscation means hide. So Perl is already a very hard language because the syntax is so complex. There's so many ways to do things. So the obfuscated Perl is even more weird, meaning they write the most unreadable code. Yeah, nope, not going there. All right, so then that code will have all these regular expressions, okay? What the hell? Let's try one of them. So I want to show you. It's regular expression city. If you love regular expressions, you should learn Perl and actually do all this yourself. Yeah, I do. Good thing that I have the the paid version. Yeah, scary stuff. Before you know it, Okay, one more time. Free service, I like that too. Okay, I just want something to load up. Okay. All right, so I think this one loaded. Look at that. Holy crap, right? That's what I mean. You need to be an expert Perl programmer or expert any programmer. Do you want to know what the hell is going on there? And then thankfully they explained that to you in English, okay? Yeah, these things win prizes, but it's full of regular expressions. Okay, so compared to all of that, our percent and underscore is actually very simple. Okay, moving on though, I just wanted to tell you that this query runs first, comes back with the result of vendor codes, and then you just find all of them, and then find the names. Exists, okay. We can take a break, in a few minutes, okay? And then today, by the way, if you notice, I had a lot to say, so we don't have a discussion today, right? So that's planned. Where's that? Up here. That's planned. But then otherwise, we'll have discussions. So I'll maybe finish this aspect and then we can take a little break. Exist is important. So exist is when you have the subquery again, but now the subquery is more like a class, meaning if the subquery comes back with nothing, right? The main query also won't do anything. So you can think of exist as only when, okay? I'll show you the example, then we can go read that. It looks like this. Do all of this only where exists, and then this. So when this happens, if this came back with some rows, then this will run on those rows. But for example, this one says, tell me all the vendors from whom it's time to reorder. And when will reordering happen? When people bought so many things that it fell below the minimum order that we're supposed to have. This literally says, so give me all the whole rows, all the information for these kinds of products, but then tell me all the vendors that actually supply all those products. So that's exactly what this does. So I want to read you so that I don't miss anything, right? Okay, like this. It's a class, it's a separate subquery. It returns true if the subquery returns any actual output. The subquery has no output at all, non-zero output, then it's true, otherwise it is false. The subquery can fail, there's nothing to return, then it's false. So then the rest of the main query, the real query running or not depends on whether the subquery returns true or false, okay? So like that. So therefore, if you want to modify, something here, right? You can do an exist first and then modify only if the exist is true. That's called defensive programming, defensive updating, defensive driving. Be careful. Don't just blindly update something. Make sure that it's updatable. So we'll use exist for that. So, where exists, when you see the word where exists, You can say such that there exists. Like when you read it like this, you read all these examples, it says such that there exists. Okay, I'll put it up in a minute. So in the first example, select star from vendor, find all the vendors such that there exists records for them in the product table where this is true. So obviously there are many vendors, and for many of them this is not true. We have to, well, you have no choice in a way. If you can find a different way to run this, then you would do it. But some other times you would find when you think it through that exists is probably the most reasonable way to express it. Then you would not worry about, the runtime efficiency of it. What is the benefit of the main query is going to run? No, the main query will not run on empty rows. That's exactly the whole point, Molly. The main query would just silently do nothing when empty comes out of exists. Yeah. So exists will tell the main query basically to run or not. Okay, that is basically what it does. So the next example is a little better than that one. I think I'll explain to you. Insert into context. So you want to insert something into a context table, okay? But then what are you inserting? Like this. Okay. So I want to insert. I'm only showing you this part, and then you figure out this part, okay? Because there's a little bit more here. Okay. So you have a context database, like a Rolodex on my phone that I want to call people. And in my contact database, I want to put contact ID and contact name. So that's the least that I need to put. But then what are my contacts? Where is my contact list going to come from? It's going to come from this query, from the suppliers. I'm basically putting a subset of my suppliers into my contact list. I want to call them often, but not all the suppliers. I want to do this. When I say select star from orders, I go in the orders database of all things, and every order has a supplier ID. So I order something from Amazon, right? Then there's somewhere that says, who is the supplier, who's the person, who's the vendor that made my thing that I ordered. But so then the thing that I ordered should be an existing supplier. I might be ordering from suppliers that don't exist, right? So this makes sure that something that is currently being ordered is in a supplier list, and those suppliers are what go in context. So in the end, what this is saying is, make me a list of all the contacts from which people are currently ordering. Yeah, exactly. So exists is loosely more like this. Yeah, it is like exception handling in a way. Yes. So the main query's result depends on what happens here. Sure. Okay, so then that is really what it was, okay? So you're only picking from these current orders suppliers that actually exist, and then they go in my contact database. Cool. So this prevents me from putting everybody from whom people are not currently doing business. Because maybe I want to reward the suppliers. I want to order more from them, but I want to find out first of all who they are. So this query does it. This one does the opposite, okay? So this one actually says anybody who are currently ordering from, people are ordering from, delete them, okay? So for whatever reason. In fact, there's also something called where not exists that's much, much more useful than this. Suppose you put a word not here, where not exists, then you're doing something supremely useful. You're basically saying, throw away all the suppliers that are currently not being useful to my customers. Because the suppliers that are being useful to my customers are these suppliers. Then if you do a not of this whole set of rows, I'll get the complement. I'll get all the suppliers that are not in any orders, delete them. It's much more useful, okay? So please think of, there's a not there, where not exists. Okay, but I want to finish though. Okay, take a little break. All right, so in the second example, the contact list, insert into contacts, get the supplier ID and name for all the suppliers such that there exists order IDs for them. That means currently people are ordering from them. Then make a contact of all of them. That's all. So then you figure out this middle part. The middle part is actually very cool, okay? Because there's an exists, but this one is not an exists. It's not hard, by the way, okay? So still do this part and take the result and then do that. Okay, but I'll let you figure it out. I think it's time for a break. This one, yeah. Okay, so again, what I already explained, okay? So this says I want to see who my current suppliers are. So I go in the order table, and then it says, returns all the records where there's at least one record in the orders table. Somebody's ordering from them. And this one is the not thing that I mentioned. So this will return all the records where there's no records. So I want to know, first of all, who I'm not doing business with. Then as a next step, I can do delete, okay? But if you do a select and not exist, that means select all the people that are currently not, all the suppliers that are currently not in any order. They're probably useless, but I want to find out who they are. Okay, so exist was very cool, okay? So I think we should break. All right, so why don't we do a break between 7:48 and 7:58? 10-minute break. Yeah, that is simply an alias, meaning the column name is supplier ID, but then the table name is suppliers. And we usually put a table name dot column name in case there's a doubt that the same column name exists in some other table. like a namespace, okay? This disambiguates it. Yeah. Especially when you do self queries. You check one column against another column, same table. Then you would need the table name. Yeah, exactly. That is correct. Yeah, it's just namespacing. Okay, so back in 10 minutes. All right. Stop share. Leave. Bye, Molly. Okay. Talking, Satichari. We're down to 100 participants. People left. Oh no! Come back, come back. Okay, so share. It's only 99 people. You guys are the hardcore SQL people. Now it's up to 100. Some people got up and left. Bathroom break. Not back in. Okay. So I'm gonna continue, okay? Because it's all recorded. So the selecting the value between, I wanted to show you that. The between thing that came up, right? So one of the students said, is the range inclusive? So when you have between lower value and upper value, between GPA 3.5, 4.0, then, I said it is inclusive because that way, you know that those values are being covered. So this tells you, you can Google it. Zentude is very nice, by the way. So Zentude is also just like W3 schools. They give you a list of all the keywords, and then you can, just practice it. You can copy and paste all those examples like right there, real world examples, like all that. And then make sure that that actually shows up all right. That's very neat. See, like right there, able to change things. Many are live coding. So this one doesn't seem to be, but so many examples, anymore are actually, examples that you can run right there. If not, make it be so, meaning take your own IDE. So I cannot wait to show you all the different ways in which you can practice SQL. So I'll talk for about 15 more minutes till 8:15. The last 5 minutes, we'll spend some time on just going over like different ways you can learn SQL. And the rest we can finish next class. There's no hurry really. Next class is called Advanced SQL, but it's not a full class, meaning it's smaller than this. Okay, so then just continuing, okay, we had exists, and exists was very cool. Then what about other things? So what can you do past exists? The alter table command. These are the easy ones. We can just basically talk about them. So when you say add, then it'll add one more column. Suppose you want to, have employees' birth dates, and add an extra column called birth dates. And then modify is to change the data type. Supposing you had string IDs, now you want to switch to an integer ID, and you can change the type, the column type. That is modify. And drop means just completely delete the column. These are all column operations, okay? And then you have to say alter table before you do all of this because you're altering tables. And then you can also add things like constraints. You can all of a sudden say to a column, I don't want to get people that are, like less than 16 years old. Then they can have a date restriction. Likewise, you can remove restrictions and say, this restriction is too much. I won't check for this anymore. So these things dynamically, you can make changes in the table structure, and that in turn will dictate what type of data can be in or not be in. So, these are not as important as querying, and most of us don't do all of this, okay? Mostly DBAs and people like that do it, but it's nice to know that it can be done. So how do you change the column type? You literally like this. So alter table, table's name, modify, column name, new type. Like in Python, I can say x equal to 5 and do something with 5, x plus plus what. And then I can say x equal to USC. At that point, I change the data type for x from integer to string. So it's like this. So the new type just wins and the old type just goes away. But a lot of times this will not be possible. You'll get an error if the column contains data. Because say you go from a 10 long string, meaning a string of length 10, to a string of length 5. Suppose you want to shorten it, then you might actually potentially lose information. You might end up with lots of duplicate names. So for that reason, they want to make sure that you can only change properties on an empty column. So it is up to you to store the information somewhere else and then make the column, meaning delete all the values in the column, make them all null. Only then it'll let you modify the type. This is just to protect you so that you accidentally don't end up deleting data by column modification, column type modification. All right, so then, just say modify, again, like this, another example, right? Price decimal, 9.2. So very similar. This also sometimes has restrictions where you simply just cannot modify the type. But then if you're able to modify this, what you would do, change that to maybe you're selling more expensive products. Maybe it used to be 5,2. Now you're selling much, much more expensive things. So you need a place to store all those high priced items. So change it to 9,2. Okay. So then adding and dropping. So this is the whole adding a new column or completely deleting it. Suppose you never put things on sale. Okay, you used to have very good sales and customers came all the time, but now nobody's buying things from your store. You're like wanting to like make some money, so you'll put things on sale. Sale means lower price, right? So an extra column for every single product. You might have a sale code of 0. 0 means it's not on sale at all. Oh, cool. It means full price. So sale code 1 means maybe 10% off. 2 means 20% off. Now you're forced to do that, because you're losing money. So you would add one extra column and go on manually fill in like values 0 and 2. That's how you add a new column. Conversely, suppose you don't care about who makes your products, okay? You want the whole vendor column to be gone. Just simply go on, sorry. In the vendor table, suppose you have a column called ordering table, V order. Just delete that column. Like any column you don't need, just drop column, okay? And again, sometimes, you cannot drop a column unless it's empty. So those things I don't mention, they're just implementation dependent. But I'm just telling you what the syntax for deleting is. Most of us don't delete columns. Most of us don't add columns. Most of us do select where, okay? And then exists like all the, there's something called correlated subquery, which I'll tell you next class. So focus more on the query part rather than changing table structure. They're all not evenly used, All right, so update. Again, update just means you can manually do an update. See, I gave you an update example earlier where you can have a table that is inserting some data based on some other condition, like update all the products, that cost less than $10. So for all the products that cost less than $10, make them be like 10% more, stuff like that. So that's data updates. He's doing the set operation, but based on some condition. I think that's an example. And then arithmetic operators roll back. Okay, so in this case, roll back, there's somebody asked this, So 2 updates would be like gone when you do a rollback. So rollback does affect updates. Okay, so then what does all that actually look like? It looks like this. Set. So this is where the set condition. So it means, say you have a column called sale code. You want to put only this product on sale code, have the product's ID. So then make that be 20% off. This means some machine can manually print like a 20% off label. You can go and stick it there. And then for either this product or this product, make them be 10% off. Make things be 10% off when it is made between these dates. So literally you could do a between here if you want, okay? So that means things that are purchased between those dates, maybe it's a bad batch, maybe the product is defective, so then give 10% off to customers. Or this is what I mentioned earlier. So now you want to make more money because you're not making enough money. So you think, why are things less than $50? Or if they're less than $50, can I at least make them a little bit more expensive? So then make them be 10% more expensive. It's like a variable update, X star equal to 1.1. But Oracle does not have star equal to, so the column name is repeated. But that's obvious what it's doing. You're actually making that a little bit more expensive. Conversely, you can put things on sale. You can say the more expensive items, they cost too much, people are not buying. So price is more than 50, make it be pre-price star 0.8. So that means 20% off. So these are all numbers you can play with. So in Amazon, they do these sorts of things automatically. This number is automatic based on how many products they're selling per hour or per day or per week. There's some extra analytics that is being done. And then they give you like all kinds of reports. And then these numbers are just fluid pricing, meaning they just play with numbers. If people buy too much of something, they'll keep on increasing the price until people don't buy as much. The rate falls a little bit. Conversely, if a product is stuck for a long time, nobody's buying, then gradually, they'll make the number lower and lower to see if people would buy. It's just amazing how fluid that is because it is just a number. There are limits, obviously, like stock trading, right? So within those limits, they're just playing with numbers. Okay, so then table update in bulk. This is where you can do set operations, insert operations by getting the results from a second query, a subquery. That's all it is, okay? So then your subquery should return something that the main query can accept, such as matching column names. It's all about columns, just common sense once again. And then you can do it in 2 steps, meaning you can first of all do a subquery and make some kind of a table out of it. And then line by line insert that in the main query, in the main table. Or you can combine both those operations, go in some table, fetch data, and just put it in the main table, okay? So 2 different ways I'm going to show you. Okay, so then, in other words, you're copying parts of one table onto another table. And why do you want to do that? Because otherwise it's manual, all right? So then it's like this. So you're trying to duplicate a table you already have. Okay, so you already have a table, like in here. So then from this table, actually, wait. So you already have a product table, but then now you're trying to make a new table called part. Okay, so in the part table, you call everything part. So part code, part description, part price, vendor code, primary export code. This is completely empty at this point. How do you fill it? Insert into part all of those values that you want that come from somewhere else. So I take an existing table called product, and I'm going to query like all these columns and make them be these columns. I'm literally copying what used to be called P code in this table into part code in that table. Literally copy P description into part description. It's almost like renaming your existing product table, okay? But maybe you don't want to do that. You want to keep your product table, but make a brand new clone of it, just copy it, but rename all the columns. That's how you do it in 2 steps. So the first step is just make an empty table, and then those columns fill from an existing table. Or you can combine both of them. When you combine both of them, it's all in 1 step. So create this new table called part as. As means I'm going to get data from somewhere else. As, select, again, P code as part code. So then when you do a select operation, right, I'm selecting a column, I can rename the column as something else. So the new name would go in the new table. So it's everything that we do here, but all in 1 step. So name the old column to be new column, old name, new name, old name, new name from product. So when this runs, this will just completely get a copy of the product table and rename all those 4 columns into P something, P something, P something, P something. And that will all just instantly go into part. Wow, right? It's combining both those into just one simple syntax. But here's the question. What is the problem with this? Or what is not the problem with this? The 2-step seems a little bit actually, nicer, better in a way right now. Why? Why is the 1-step worse? Or here's a hint. Even though it is 1 step, that 1 step requires a 2nd step also. Something is missing. Yeah, exactly. Primary key. Very good. So this looks like great. It's a little bit confusing. This is nicer. But the problem with this is also there's no primary key. So you have to separately set a primary key for that. It's not a problem, okay? But this is artificial. It's like a little faking. It seems like, wow, I'm so simple. But you then, oh, sorry, you only did half the work. You still need to do that half of the work. Therefore, this and this plus the primary key is pretty much the same, okay? So like this, you can always add a primary key or a foreign key afterwards, which is exactly what you do here. See, like this, you have to say alter table, add primary key, part code, alter table, add foreign key code. So rather than do 1, 2, and then 3 pieces all separate, I might as well do this. This makes much more sense, okay? Yeah, so it's really 6 of one, half dozen of the other. It doesn't matter. Okay, deleting is easy. Just drop it. So delete, drop table, yeah, the table name, and then hopefully you have backup copies, and then if you want it again, otherwise it's gone. All right, just forget the one side, like all that. And then, yes, so, there's a foreign key, the foreign key integrity violation. It means anybody that is pointing to all of these rows will all get a violation unless there's a cascade. So when you set up a delete cascade, then when you drop the table, then all the other tables that depend on this table's columns. In other words, if anybody, the primary key here is foreign key somewhere else, then all of those tables will also be affected. Otherwise, technically, they're a violation. It means they're pointing to null, right? The whole table is gone. Okay, so these, again, common sense things you can read about. So ordering, visual ordering. Maybe this all we'll have time for, but that's good. Ordering is like Excel spreadsheets, sorting. So you want to sort something by price, by first name, last name, by birthday. Just visual sorting. It doesn't change the data order in any way at all, right? Just simply something nice way to look at. So we use the word order by. Okay, so then this is separate. This is all about the whole aggregate operations. How do you make a sum of a whole column? How do you find the min of like a bunch of numbers? That's what this is about. So again, examples make it also easy. And then when you have duplicates, suppose you say, give me all the vendors that I do business with. Suppose I have 1,000 products. Every product has a vendor ID, right? But I only have 10 vendors. But when I say to all my 1,000 products, give me a vendor ID, I'll get 1,000 values. But it's really same 10 values repeated over and over and over. But I see 1,000 of them. It's confusing. So then I have to tell the system, come on, just give me one value only one time, like vendor ID, make it unique. So then I'll only get a smaller list of 10, right, as opposed to 1,000. You would do that by saying unique. Okay, so examples. Order by. Literally do an example and finally say order by. After where? Order by. And you can order by many columns. So it'll sort by first one column, sort by second column, sort by third column, what. It's exactly like Excel, okay? This is for numerical or characters. You can do ascending order, meaning go from small to large, or descending large to small. Okay, pretty straightforward. Again, it's called cascading when you have many columns because it's using say the first name to sort people's names. And then for two people that have the same first name, use the second name to sort. If they have the same second name, use the initial to sort, and so on. So it's cascading sorting. You've seen all this in Excel probably. Okay, so let's do the price example. Okay, how do you see the products in your store when you say just price, it's going to go from small to large. When you say descending order, it's going to go from large to small. Okay, so select product code, product description, product invoice, date price from product, order by price. If I don't see order by price, I'll see all kinds of numbers, and I have to manually go through them and see that is smallest, that is the largest. But when you say order by, it is so easy. Just look at the top, look at the bottom. When I say descending, then it'll go backwards. All the rows will be upside down, okay? Just like this. You can do that yourself. Just say DESC. And then, so if you have more than one that are similar, like same first name, right? Same last name, same first name, different initial. And I can do it like that. Sort by last names first. And if the last names are the same, then sort by first names. And if they're all also the same, then sort by initials. So it sorts in this order. 1, 2, 3. Again, very simple. Distinct. So distinct is when you're tired of looking at too many of the same thing. You don't even know how many distinct things you have because it's too many of these repetitions. Then you're saying for every repetition, count the repetition only as one time. Literally, my 5 vendors that supply me 1 million products. Just give me 5 IDs, not million IDs repeated. Distinct keyword, just say distinct. So all you have to do is say distinct column list. Therefore, in that column, it'll make sure that only distinct values appear. Okay. Like this, literally the example I showed you. So if my store has 10,000 products, okay, if I just say select V code from product, then I'll get a table that has 10,000 entries. But except these 6 names would be repeated like 10,000 times over and over and over, right? But instead, if I say select distinct V code, then I'll have a smaller table, meaning it'll throw away all the duplicates. Okay, so then I'll only get all these possible distinct values. Note that null is also a distinct value. Okay. In fact, nulls are multiple distinct vendors, but it collapses all of them into one distinct. So null is a bad thing, right? It means we have no idea how many nulls we really have, but null is counted only once. Because it can count null only once. Nulls are not good. Aggregates are simple, super simple, and then maybe we stop after this. Aggregates just simply mean these simple words followed by in parentheses a single column name, and the column will be counted. The column's lowest value would be found. The column's highest value. The column would be added up. The column's average would be found. I can do all of these for scores and stock prices and things that I own, stuff like that. Aggregate function. So in this one, after you do a distinct, right, then I'm too lazy to count manually 1, 2, 3, 4, 5, 6. I can even tell the system to count it. We won't count nulls. Then you say count parentheses distinct like that. Oops, going backwards. Here. When you say select count distinct V code, then you saw V code produces 6 values, so count will turn that into 6 like that. Or you can do this, you can say select count distinct V code. So who are all the vendors that are supplying me things that are less than $10? How many such vendors do we have? We have 3 vendors. Select count star. So star is just simply, basically count every single row for whom the product is less than $10. Okay. So then that is 5. Cool. Max min. Again, what is the most expensive item in my store? 256. What is the cheapest item? That. And then this is also very cool. So now this one says, I want more information about my max things. So you have to do it as 2 queries, okay? Suppose I want to know what is the name of the, the most expensive thing. I first have to do a max price. Okay, look how cool this is. So this one just simply gives me the max price. Remember, there's a number, there's no closure, there's a numerical value. The numerical value is 256. Then you glue this other thing on, it says go to my whole store and find out anytime the price says 256.99. And then for that product, give me the name and the product code and the price. This is just to verify that this is true, okay? But that's so cool, right? That it has to be 2 different queries. You cannot make them into 1 query. Plus, if there's more than one product that costs exactly 256.99, they both would be named. Because this query is going to just simply do an if statement based on that. But it has to be 2 different queries. Okay, so then one last example, and then we can do like SQL, or maybe we'll do SQL when we come back, like how to learn SQL. This one says, again, so then again do this. So take that maximum, find out all of the different values. Like I own 10,000 products in my store. For each of the 10,000 products, tell me how many of each product I have, how much each costs. So multiply. Take the largest of those. Then that would then match certain products, right? Then tell me what those products are. So this is a little bit better than just simply going by the price. So this is going by value. So tell me all the products that cost the most value in my store, okay? Maybe only one product, or miraculously many of them that have exactly the same number. Tell me what those are. Whereas this one is only going by price only. Do you know what I mean? Say this one is, $10,000 is the most expensive item in my store. It's going to find it. But this will also find something that is only worth $1, but I have 20,000 of those items. Then 20,000 times 1 is 20,000. So this will be more than the 10,000. So you'll get a different answer. Look at something that is so cheap, but I have a ton of it. I probably need to get rid of it. Okay, so two slightly different queries. Okay, I'll tell you what. So this is so simple, right? But we can come back to it, right? This one, I'm just going to keep going. Okay. So this one, till we run out of time, okay? All right, so now comes the time when I have to tell you how many different ways can you do this yourself, because you must do all this hands-on. Why not? It is fun. You can create tables, enter data, and do queries, because in the end, that is all it is, okay? So you have tables, empty tables, fill with data, do queries. It's basically exactly like data science, right? So any data science operation. What? Put your right hand out, put your right hand in, and you shake it all about. You do the hokey pokey and you turn yourself around. That's what it's all about. The hell? Okay. We're singing hokey pokey because this is really what it's all about, okay? That's what it's all about. Operation after operation, same thing, no matter what you call it. Data science, machine learning, even very similar. So take a table, an empty table, put some data in. By the way, you can do like left leg, right leg. You can keep going. Do it afterwards. So take a table, fill with data, ask something over and over and over. Three ways in which you can do it, you guys. So you can get a database and then do SQL on it. On a browser page, it means the actual database is on a server. And then you are just simply doing browser-based stuff. Like W3 Schools is a good example. Or you can actually get Oracle on your laptop. I definitely I recommend Oracle. This Oracle Lite. It's great. Okay, just put it on your laptop. Then everything would be local. Or you can use clouds. There's AWS, there's Azure. There's many clouds that have databases. So I'm going to show you a little bit of all of them. Okay, till we have no time, and then we continue next time. So SQL tutorials I already showed you. IDE1 is a thing that is a multi-language, IDE, meaning you can do Python, Java, JavaScript, C, so many different ways. Yeah, actually, DataGrip is a good one. So is REPL. I think Replit also has SQL. But look here, you can just switch it to anything, right? So pick SQLite. That's like a version of SQL, basically SQL. So then please practice things that I tell you. Make a new little table, like do some between commands, and then just run it, okay? So that's a great way. I'll add DataGrip, definitely. Thank you for that. Okay, that's one. SQL Fiddle is again a place where it's in two steps. On the left-hand side, you create tables and then put data into them. This build schema. On the right-hand side, you run the SQL, which is actually do the querying. And the nice thing is when you do that, you will actually get like a key here, like a perma key, meaning it'll give you a URL that you can send to anybody in the world. And when they click on it, your queries would come back. So this way you can make it remember what you did. You can switch between different SQL implementations, but just stick to what the hell. It's what it looks like, okay? So like this. So create table if it doesn't exist and put these 3 columns and insert some rows and just say build schema. Then say schema ready. Then you can actually do a command here. There's a join that they're doing, okay? Run SQL. Wow, instantly. And then you can start playing with this. Look, right, they just play it. It's not null, okay? I didn't see what this is, but you can try it. So that's very neat, right? You can instantly run it. And so, it's already 8:21. I want to show you 2 things and I won't rush it. One is if I go on query dependency, I fixed my typo. That's all it is. Just fix my typo here. And next thing that I want to tell you, like that. See, fixed it. That's a typo. Is if you go back to your join that we had before, I put a little clip in the join thing. And maybe I should put it up on Piazza. I don't know. I'll look for it for just 1 second. If not, we'll let then people go, okay? Meaning I made a little clip that illustrates visually what the joins look like. That's really all. It might be in, where might it be? Relational model. And look there. Okay. So just really fast if it came up. If it doesn't, it's totally okay. Yeah, so maybe at the end of this, joins. Yeah, this one. So Yash, sent it. So I'm going to, credit him for that. Joins, just look at this little movie. This was done in the R programming language, Tidyverse. Hey, wait. Just click. Oh, there it is. Okay. So you see left join, right? Left join means you leave a gap, like on the right. So, and then right join is the opposite. You'll get all the, rows on the right and so on. So just watch it, you'll know. And I put everything twice so you can really see it. So two very simple tables. Left join means I want all the left rows. So on the right, I can have holes. Right join means I want to have all the, again, rows on the right-hand side. And then on the left, I can have holes if I want. Okay, so just watch it, all right? That's all. So we're going to stop. And then I'm going to finish the rest of the SQL commands and more SQL commands next time. You can easily finish it. Why does SQL syntax change for different DBMSs? It should, so that is why if there are any changes, they're minor. The standard says you should not change it. But different vendors have a little latitude, a little permission to do some changes.
It's really because the SQL standard back then had only very limited functions, and every vendor wants to add value-add stuff into SQL, which basically becomes individual dialects.
Yes, I love it. I love that answer. OpenGL did the exact same thing in graphics, okay? So I make a new video game controller that has some amazing, XYZW, access, right? So then Microsoft would write a driver for it, right? But then they've screwed up OpenGL. It's called a vendor-specific extension, okay? So likewise, SQL also does have vendor-specific extensions. They do something pretty cool with the product that you cannot do with some other product, but it breaks the standard, I agree. Downloading Oracle is probably the best. So, if you go through that list that I put up, and I'll go through it again later on, there are 3 different ways. So please get Oracle. All the links are on there. But if you read the page carefully, it'll outline many ways in which you can learn SQL yourself. And that is what I would do if I were you, right? So just pick one of them. Don't get too bogged down. We do the Cloud IDE. There's one called Live SQL. Okay, so livesql.oracle.com. So in Live SQL, you can type things and they'll remember it for you. So when you go in, they'll have all your hundreds of scripts that you've stored over time. So that's also a pretty neat thing that you can do. Or you can do RDS. We'll revisit this another time. So when we come back, we'll go through this page and then finish up a tiny bit more. And then I can tell you why SQL looks like a programming language. You can write functions actually, and you can write like what's called procedures. So do a little bit more. All right. Okay. So in the meanwhile, good luck with your homework. Finish it. And do a good job if you can, because you're going to use SQL along with it. So don't make bad tables. All right. Bye, you guys. Vignesh, Mohammed. Okay, everybody. Stop sharing. Yash. Utkarsh, Malaki, Vaishnavi, Karina, Akash, Bowen, Ichun, Surabhi, Shreya. Hey, got you all. Okay. Bye. Rangapriya. Kartik. Okay. I'm gonna leave. Leave.
Hey, just
bye bye.
Second.
Oh, someone had a question.
Yeah, it's just that when we'll work on anything in this course, we'll have the flexibility to choose our database, is it?
Absolutely.
Okay.
Yes, so we won't restrict you to anything at all, and you will tell the TA what you chose. Hopefully, it'll be from the standard list, and then usually we'll never restrict you. Okay. Yes, gulab jamun time. That is correct. All right. Bye, everybody.